EigenVectors. Let's put our hands together as we welcome Dr. Awelewa.
Okay, so I have this task before me today. My job has been made simple by Professor Adetiba by giving me just three topics to take under this session. I'm going to be talking about vector spaces, linear transformation, EigenValues, and EigenVectors. These are extremely important in linear algebra, and linear algebra is extremely important in so many fields of endeavor. What is linear algebra? What is linear algebra? Linear algebra involves the use of techniques for describing linear systems and their functions, together with their representations, operations, and manipulations using vector matrix symbolism. Vector matrix symbolism. We transact in vectors and matrices in linear algebra. That is our currency. We employ vectors and matrices to describe many scenarios, many applications, many phenomena. These are extremely important. In engineering, natural and social sciences, in art and humanity, virtually all human endeavors, linear algebra is very, very essential. What are these vectors and matrices which are the heart of linear algebra? They are actually structured arrays of numbers representing objects or phenomena or processes or systems. And they are very key. They are very key to what we do in linear algebra. The tools of the matrices, for instance, those who are in image processes, those researchers who are working in image processing, they will know that the images are simply matrices of pixel values. Okay, you have your image, and then this image is worked on. Okay, it's worked on, and then you have pixel values. These pixel values are actually housed in a matrix. Okay, and then this matrix can further be processed in order to extract important features of this of the images that have been worked on. So vectors and matrices are extremely important. Also, in linear regression model coefficients, finding the coefficient of a typical linear regression model actually boils down to solving a system of linear equations. And this system of linear equations is also a matrix vector representation. So we have a system, we have a architecture which can be described by linear equations. These linear equations can be transformed into vector matrix for further processing. As soon as we have the representation of the system in vector matrix expressions, then we can do a lot. We can do a lot about the system. We can reduce the size of the system. We can increase the size of the system. For instance, those who are, again, in machine learning, they normally carry out what is called dimensionality reduction. I know Professor Adetiba will talk about that under principal component analysis. We do serious dimensionality reduction. We have a very large system we want to analyze. At times it becomes cumbersome or even impossible dealing with this very large system. very difficult. What we normally do is to see how we can reduce this large system. We reduce the model into a form that we can actually handle, into a form we can process, into a form that will give us a very good advantage, in creating algorithm, in creating a design solution. So vector matrices are extremely important. Similarly, we know that what we call synaptic strength of artificial neural networks, this weight between neurons, we know these weights are extremely important. When we say we train, okay, we're actually adjusting these weights. We're actually adjusting this weight. And these weights can actually be represented as matrices. They can be represented as matrices, and then the algorithmic training that is done. It's all about forward and backward passes. And this involve a lot of matrix multiplications and other linear transformations. Okay, so vector matrices are extremely important. Again, EigenValues and EigenVectors, which are also important concepts in linear algebra, are also very useful in so many systems. For instance, in image compression, EigenValues and EigenVectors are very important. Feature reduction, very important. In signal processing, for instance, if you want to reduce noise, we can also apply this concept, EigenValues and EigenVectors. Because, for instance, EigenValues actually describe key parts of a system. In fact, they capture the frequency nature of the system. If you have access to the EigenValues, then we can represent the system in so many ways. We represent the system in so many ways, in ways that will be useful to what we want to do, the design we want to carry out, the architecture we want to work with. Okay, so these are extremely important. Even those who are working in medical imaging too, I know they do a lot of image reconstruction and then denoising. Okay, there is a concept that is also very useful here, the concept we call SVD, which is a singular value decomposition. It's also important in linear algebra. This is also very good. Again, machine learning model understanding, interpretation, we also need SVD, singular value decomposition, EigenValues, and EigenVector. For instance, we want to extract important features or components that contribute to a particular machine learning model. SVD, EigenValues, and EigenVector, give us the benefit, the opportunity to be able to do this. So vectors, matrices are key. They are very key in so many applications. Again, if you want to develop algorithms, if you really want to develop algorithms, I tell you, you need to understand some of the fundamental concepts in linear algebra. The fact that vector matrix representations can allow you to develop an algorithm in a compact and then efficient way is something that is very useful, something that is quite appealing. Okay, so I want to encourage all of us that this should not stop here. This should, even after this workshop, after these sessions today, I encourage everybody to still explore some of these important concepts further. It doesn't stop here. In fact, if you need to, like Professor Adetiba said the other time, that some of the facilitators actually form a circle of experts that you can actually consult at any time. If you want to contact me on some of these concepts after this workshop, you are very, very free, because it doesn't stop here. Linear algebra is a vast field that you can't cover. You can't cover in just one session of a workshop. What I'm going to do here is just to open your eyes to some of these important concepts and discuss extensively, okay, one or two of them that are extremely important. And thank God, Professor Adetiba actually shows these important ones intelligently. For instance, EigenValues and EigenVectors, very, very, very important. So I'm going to show you how this is done today. How do we calculate EigenValues? How do we calculate EigenValues? EigenVectors, why are they useful? I'm going to expound on this today into a closed compact that we call a vector. So a vector is a finite collection of numbers. And then vectors have spaces, vectors have relationships, and vectors connect. We use spaces. We use spaces to describe vectors. A particular space we contain is so many vectors, another space we contain so many vectors. For instance, in a real dimensional space, a vector V, this vector V, okay, is an element. It's an element of this space. This space is a set of so many vectors, and then this space is represented by this n. You can see this n right here. This actually connotes this vector is an element. It's an element of this space, this n-dimensional space. Okay, this is a space of n-dimensional vectors. A space of n-dimensional vectors. For instance, look at V here. We have V1. V1 is the first element of V. V2 is the second element, and Vn is the second element. So this vector V has n elements. N elements. So we say it's an n-dimensional vector. An n-dimensional vector. So in a general set like this, we have so many n-dimensional vectors, so many. So this vector V, this single V now, is just an element of this space. It's just an element of this space. It's just like a drop of water in an ocean. An ocean represents a dimensional space, an n-dimensional space of drops of water, n-dimensional space. This V, vector V, is just an element of this space. For instance, if V is made up of a V1, V2, and V3, V1, V2, and V3, that is 3 elements now. So we have V, we have the first element V1, the second element V2, and the third element V3. Then this vector is actually a 3-dimensional vector, okay, that comes from a set of all 3-dimensional vectors. Okay, so this new ways. Okay, it's just take your time and follow. Okay, and follow. So we have a Coulomb vector and a row vector. Look at this one, this vector V. This is a Coulomb vector, the way it is. It's a Coulomb vector. Okay. Why is it a Coulomb vector? Because it is arranged vertically. You can see is a Coulomb. And then we have the other one, which is called a row vector. Okay, we have it, which is called a row vector. So this Coulomb vector can also be seen as an n by 1 matrix. An n by 1 matrix. You can see it. How many rows? N. Okay, n rows. 1, 2, okay, 3, 4, up to n. And then how many coulomb? Just 1 coulomb. So we can also see it as an n by 1 vector. N by 1 vector. Why it's a counterpart row vector can be seen as a 1 by n vector. A 1 by n vector. Okay, now what is a linear vector space? What is a linear vector space? Like I said before, a vector space is actually a huge collection of all n-dimensional vectors. A huge collection of all n-dimensional vectors. Okay, if n is equals to 2, then the vector space becomes a huge collection of all 2-dimensional vectors. Okay, if n is equals to 3, it becomes a huge collection of 3-dimensional vectors. Okay, and that is why we are using space. You can see it, vector space. That is a space of vectors. A space of vectors of a particular dimension. Okay, we have 2-dimensional, we have 3-dimensional, we have 4-dimensional, up to n-dimensional. Okay, depending on the number of elements or entries in this set. Okay, what are the important features, important properties of a linear vector space? What are the important properties of a linear vector space? Again, let me state here that these vectors are not just arbitrary collection of elements or objects. No. They actually represent systems. They represent devices. They represent processes. Okay. For instance, in engineering, and electrical engineering, you know, we handle circuits, we handle systems. Many of our circuits and systems can actually be reduced to all of these vector matrix expressions. Okay, in fact, I call, you know, when I see this matrix, I call them systems. In my own case, I call them systems, okay, because they actually represent systems. For instance, a system of linear equations, and that's why we say when you have simultaneous equations are not arbitrary. They actually represent system, and that is why we call them systems of linear equations. Systems of linear equation, because they actually represent systems. So I don't want you to see this as just juggling numbers around. No, not juggling numbers around. They are very, very important. They represent devices. They represent systems. Like Professor Adetiba said before, if you can understand or grasp these concepts, you can actually do a lot in your research. A lot in your research. Okay, for instance, I remember when Professor Adetiba was doing his PhD research. Okay, in those days, there was a time he encountered a challenge with, you know, coming up, okay, finding a particular algorithm to use for his work, genomics work. He looked around, he couldn't find. He had to develop one himself. He developed one algorithm himself, which worked very well. It was very fantastic. Very, very fantastic. Why? Because of his fundamental understanding of some of these things, he was able to do that. Okay, there are times that count algorithms, count programs will not work for you. You may have to develop your own, okay, to use for a particular purpose. And that is why you have to, you know, get yourself familiar with some of these important linear algebra concept. All of the machine learning algorithms, ANN algorithms, they are very, very powerful. And then at their heart, at their heart are actually matrix equations. Matrix equations, expressions, representations. So again, don't see this as juggling numbers around. Again, these numbers actually represent physical systems. Okay, so as I was saying before, every vector space has unique characteristics or features, or all vector spaces have these unique features and characteristics. Okay, these are explained below. These are explained below. Okay, number one, if we have two vectors from this space, again, don't forget when I say this space, okay, this space might be two-dimensional, this space might be three-dimensional, this space might be n-dimensional. For instance, look at this vector u, look at this vector u, look at this vector v, okay? These two are from this x, this linear vector space x, okay? This set of all n-dimensional vectors. So these two vectors are from there. Okay, so the first important attribute is if you had two vectors in a space, in a linear vector space together, you should get a vector that is in that space. Okay, this is very, very important. All linear vector spaces obey this. Take two vectors from here, from this space, add them together. The result is also a vector that is in that space. That is an important attribute, okay? The second important attribute is if you multiply, if you take a scalar or a constant number from a field of real numbers or complex numbers, this is the field F. Just take a scalar parameter, and then multiply this scalar parameter with a vector, any vector in the space. What you get is also another vector, which is in that space X. You can see the way it's written here. Okay, U is a vector from the space. Alpha is actually a constant value. Okay, a constant value from this field of constant numbers. Okay, so what you get is another vector, which is an element of the same space. Okay, these two properties are called closure property. Every linear vector space satisfies this. Otherwise, it is not a linear vector space. Okay, they satisfy the closure property. We call these addition and scalar multiplication property. Addition and scalar multiplication property. You can see U plus U and V together. Okay, we give you U and omega together. Okay, if this situation holds, okay, for this vector space, it means that definitely V is equals to W. And that is what we have here. It implies that V equals to W. All right. This is equivalence. The next one is if you multiply alpha, okay, by a sum of two vectors from this space, okay, this operation is also valid. Okay, this is a linear operation. This is a linear operation. You multiply alpha by each of the terms in the parentheses. Okay, so UV come from X and alpha is a constant value. The next property is this: if you add two scalars together like this, okay, and then multiply the result by a vector U, okay, the result is the same as multiplying individual vectors together and then adding them as this: alpha U plus beta U. Okay, now alpha and beta are constant values. Again, multiplication of alpha, beta, okay, by U also result in this. okay, alpha, beta u. So you can move these things around, all right? These attributes actually characterize all linear vector spaces, okay? And then the last two are these, okay? You multiply one, and then a vector in that space together, you are going to get that same vector, okay? Some of these attributes look actually trivial, okay, but they are not. By the time you start, start reasoning about how to combine vectors, how to find the rank, how to determine linear independence, linear dependence, then you will know that some of these attributes are actually not trivial. They appear trivial now, but it's good for you to actually understand them, okay? The last one here is this zero vector. The zero vector is also an element, okay, of that vector space. As you can see, this is not a scalar zero place. It's not a scalar zero, okay? This is a zero vector. This is zero vector, okay? All the elements are zero. So it's also an element of this vector space. So zero vector is an element of a linear vector space. Like I said before, the closure property is very important to all vector spaces. And this closure property is simply addition and scalar multiplication, which I showed you before. Addition and scalar multiplication. All linear vector spaces obey this. They obey this, okay? Yeah, let me mention this before I leave here. The simplest vector space has just one element, and it's just this vector space, okay? You can try all of these properties, all of these features. You can try it on this, all right? You will see that all of these features are obeyed, okay? Although it's a very simple one, very simple vector space. Are we together?
Yes, we are. I want to
Okay.
assume that everybody is,
Yeah.
but you will also allow feedbacks in case persons
Yes,
want to.
I need that actually, so that I won't just say, I'm the only one here, so I really don't know. I'm not seeing.
So in case anybody has questions, you can just raise your hand while the class is ongoing, and
Okay.
comments can be posted on the chat box by those online.
Yeah, thank you, Prof.
Okay.
Okay, so what are some of the operations and properties? Some of the operations and properties of vectors. Okay, they are this. We have a transposition. Okay, if a vector is an element of an n-dimensional space, you can see again, V is an element of this n-dimensional space. Okay. All right. So it's transpose point here. You can see this n. Okay. This n is 1 by 1, meaning that it has n rows and 1 column. N rows and 1 column. Okay. You can see the way it is written here. V1, V2, Vn is that vector. It's a column vector. N by 1. That is what we wrote here. Okay. Its transpose is simply this. Okay. It's just to change it. All right. Okay. V11 becomes V11. V12 changes to V21 and the etc. Okay. You can see it. Then you can see the row. If we have it as a row like this, it transposes is this. Okay. Column. All right. That is transposition of a vector. Okay. And of course, in Python has a lot of a lot of modules. Okay, functions, commands that you can use to carry out some of these things. Okay, I have on vectors here. Let me see. Okay, on vectors here, I've created row vectors, okay, Coulomb vectors, then I've transposed them, okay, I've found the length of the vector, okay. We can see this. We see V, this is vector V. Thankfully, Professor Adetiba introduced some of these things yesterday. Okay, so I think my job is also easy again today. Let me also add this here. You know, you can also use a Anaconda navigator. I don't know if a number of us are familiar with that. You know, Anaconda navigator has a number of these IDEs, okay, that you can use to develop your Python codes. For instance, I'm personally using Spider from Anaconda navigator, so you can do a lot of your, Python coding there. Okay. So vectors, this V is defined, this U is defined. Okay. All right. Then we'll create Coulomb vectors. Okay. You can find the transpose of R. You can see here R dot T. This is transpose. Okay. And then you can, okay, you can also transpose this. Okay. All right. This will also transpose vector V. Okay. To transpose vector V, a row vector. We can find the length of the vector len, okay, and then you can print. You can print. Okay, you can print. You can print all of this. Okay, this is good. See, Python is giving me an error here. It's telling me that this is not acceptable. You can see this opening quote, and this is right here. Okay. All right. Okay. I adjusted that, and then I have this. And then I have this. Okay. So we have a vector, and then the vector is transposed as expected. Okay. We also do these elementary operations, addition, subtraction. Okay. If there are two vectors from this space, this linear space, okay, we can add them together like this, or subtract. U plus or minus V, okay? U plus or minus V equals to W. All right. I want you to look at this. I deliberately included some of these things because when you are reading papers, when you are reading scientific papers, okay, these are, you'll be wondering what are these? They are nothing. These are ways we speak. These are ways we express our ideas. Okay, some of these mathematical related fields in engineering, and I know in sciences, natural sciences, these are also applicable. Okay, you see, you add U and V together, we are getting this W. W again is an element of this. Why? Because U is an element of this, V is an element of this. So when you add U and V together, the vector you get is also an element from this of the same dimension. Okay. And then each element of such that, okay, Wi, that is each element of this W is simply corresponding elements of U and V added together. Corresponding elements of U and V added together, you can see, okay, Wi equals to Ui plus or minus Vi. For I equals to 1 to n. Okay. And then scalar vector multiplication. Again, if we have a scalar from, okay, R, this set, this space of one-dimensional space, can you see now? This is space of one-dimensional space. N has turned to 1 now. It's 1, okay? So it's a scalar from here. And then we have a vector from this n-dimensional space. Okay, so if you multiply the two together as this is what we have. Okay, similar presentation to this, but in this case now, V is being multiplied by alpha. Okay, I know we can follow that. All right. Here, I also created two vectors. Okay, I had them together and multiplied. Okay, the result by alpha and then printed the result. Okay. Another property is inner product. Inner product. Okay, the inner product is also represented as dot product. Okay, and symbolically represented as this dot. Okay, at times we use this. Okay, this angle bracket, you can see it. See the first vector, comma, the second vector. Okay, so what is this inner product? It's actually a scalar operation. It leads to, the result leads to a scalar. All right, look at the way it's done. Okay, u dot v is the same thing as this angle bracket u comma v. Okay, angle bracket closed. Right, it's equivalent to this also. U raised to power t, that is u transpose times v. It's the same thing as this. Okay, don't forget that u and v are Coulomb vectors, please. U and v are Coulomb vectors. Okay, v is a Coulomb vector here, n by 1. U is also a Coulomb vector, n by 1. So in order to find the inner product of this u and v, okay, we transpose u and then we multiply that, okay, with v. So that will give us a scalar. The result is actually a scalar. Are we together? We can actually find v transpose u also. You have the same result. Okay, that is inner product. And then you can see it here. Ui times vi. For I equals to 1 to n. Okay, it's the same as this. The first element is 1, u1, v1. That is the first element of u multiplied by the second element of v, first element of v, plus u2, v2, plus u3, v3, up to n. Okay, that will give us the inner product of two vectors. We actually use this to compute the length or the size or the magnitude of a vector. That is to determine how big a vector is. What is the size, the largeness of a vector? We use inner product to do this. Okay. Another property is an outer product. Okay. Inner product, outer product. The outer product is represented as this cross. Okay, cross. All right. How is it done? How is it done? Okay, u cross v is this u times v transpose. I want you to pay attention to this here. U times v transpose. U is a Coulomb vector. U is a Coulomb vector. While v is also a Coulomb vector. But transposing it here, we change it to a row vector. Okay, so we are multiplying each element of u, okay, by all elements of v to give us a matrix like this. Look at it. The first element of u is u1, is multiplying the first element of v, is multiplying the second element of v, see u1, is multiplying the last element of v. Okay, that gives us the first row of a matrix, you see. Then we take the second element of u, which is u2, and multiply it again by all the elements of v. You can see it, u2v1, u2v2, up to u2vm. Okay, up to the last element of u, which is un, multiplying all the elements of v like this. Okay, this is an outer product. Okay, some of this outer product is also extremely very useful. very, very useful in signal processing. It's very useful in image processing, you know, even machine learning, very useful. Okay, I believe Professor Adetiba will mention some of these applications to you, but we have started this race now. So I believe subsequently we can discuss you know, some of these things by looking at the algorithms that are actually running in machine learning. Look at each of these algorithms and break them down and analyze them. Okay, so that we begin to familiarize ourselves with this, and then see how we can also build and develop our own algorithms, just as others have done. Professor Adetiba mentioned something yesterday which was very interesting. It caught my attention with respect to those who are working, you know, the limited number, infinitesimal number of people, okay, that are actually doing serious business with, you know, with AI. A lot of people just talk, but they know jack about AI. There are only very few people are actually building and doing research in AI. Even those who are doing research in AI, some of them also are also operating on the surface. You don't really want to do a whole number actually not, you know, dealing with the algorithm development. It's also a very algorithm development, architecture development. Okay, it's also a very good. It's also a very good thing to do. I believe Professor Adetiba and I can see how we can you know, further this line of research. How do we also develop you know, algorithms, AI algorithms? Okay, which are very, very useful. So back to outer product now. Okay, we can also do V and then U transpose, but the relationship is this. You can see U times V transpose is actually the same thing as the transpose of V times U transpose. Okay, that is the connection between the two. You know, here, remember, I told you that U transpose V will give you a scalar. Similarly, V transpose U will also give you a scalar. In this case, either U transpose V or V times U, V transpose times U, okay? Either here, but in this outer product, this is the relationship, okay? All right, U, V transpose is the same thing as the transpose of VU transpose, okay? Same thing as V times U transpose, okay? All right, again, I have some Python, you know, Python code right there for.
Hello, Doc.
Hello, Prof.
There's a hand is up. Julius Odonuga's hand is up. Meanwhile,
Okay,
before Julius comes up, I think you may also want the student to run this code on their own so that they see, especially this inner product and that outer product.
Okay.
Maybe you can just, if your slide is sent to the WhatsApp group, you can send your slide to Dr. Oshin. Then
okay, let me do that right away, please.
That will help them to follow through. And I also want to remark, thank you for digging into the fundamentals, Doc. I didn't expect anything less. And
Thank you, sir.
To the students, you will be, I'm sure you have been reading some papers, maybe IEEE transactions, and after reading like 2 sections, you want to run away because they don't talk in natural language the way ordinary writing happens. They speak mathematics. So if you want to get your papers into the Q1 journals of this world, into science, into nature, communication, into very strong Severe, this is the language. Please pay attention, ask questions so that we are all speaking this language together. Thank you. I just want to pass that across.
Okay, thank you, sir.
Julius is raising his hand.
Okay, Julius, please go ahead.
Thank you, sir. I just want to ask, what's the relationship between, is there any mathematical relationship between inner product and outer product? Then I also want to know if you can give scenarios where outer product is very useful, where it is being used. And I also want to know what's the shape of, what's the end result, the end result shape of outer products. I know that for inner products, if you multiply probably P by Q, multiply by M by N, you get a P by N matrix. So for outer products, what shape do we get, or what do we expect?
The outer product is a matrix. There is really no relationship actually, because one is a scalar, one is a matrix. The inner product we gave us a scalar. Okay, it's just like I want to find the length or the magnitude of a vector. Okay, but the outer product is actually a matrix. Okay, again, if you see, I want you to see this. Okay, you see U1, all right? You see V1. Okay, U1 is a scalar, V1 is a scalar. Okay, so the result here is actually a scalar. So the result for each of these product is a scalar, you can see. So it forms a matrix. For instance, look at U. U here is n by 1. Okay? U is n by 1. Look at what we have. Look at our definitions before. U is actually a vector from a set of all n-dimensional vectors. Okay, while V is a vector from a set of all m-dimensional vectors. Okay, so finding the outer product of this will give us this. Look at it, U, n by 1 here. Okay, can you see n by 1? All right, if you multiply this, look at it, V is n by 1. Okay, can you see that? So if you transpose it, it changes to 1 by m. Okay, 1 by m. So you are multiplying n by 1 and 1 by m together. So the result will give you n by m, which is a matrix. Okay, which is a matrix. You know, this is actually used in in a number of optimization algorithms. I don't know if you are familiar with some of this in okay. I know in training an artificial neural network, that is in finding an optimal set of values for the synaptic strength, that is the weight, you carry out some optimization. Okay, the number of optimization algorithms are used in this case. For instance, I know of this gradient descent. Okay, it's a very good algorithm which you can use to actually find the optimal values of the weights. Okay, right? This, in manipulating matrix equations, matrix expressions. Okay, you just come across some of these where you have to present your algorithm in a particular way. Okay, they put together to present their ideas, and then okay, the solutions they are trying to proffer. Okay, all right. So this is a matrix, the other one is a vector. Okay, the next one is norm. Okay, norm, the norm of a vector. Yeah.
We have one more question.
Okay.
Good morning, sir. Thank you for the presentation, sir. My question has to do with
who is speaking?
Shobola, sir. Shobola Gabriel.
Okay. Oh, Shobola. Good. Good.
So the question has to do with the coding, the code you wrote for how to find the column vector. So I noticed it's like you created a sub array or a sub list. You use a sub list to create that column vector. So I want to ask, is there no other way for you to use a single element, like a single value, real number, to create that instead of using a list with a single element inside of it. Just like you want to do it in MATLAB, for instance, you don't need to use a sub list. Just use just ordinary real number. So is there no way you can do something like that in Python instead of using sub list to create a column vector? That's my question, sir.
No, yeah, Subola, thank you. There are so many ways. For it, there are so many ways you can there is no one rigid way, okay? All right. So I believe that we can we can choose the options that are actually best for us, Subola. There are so many ways we can handle this. Like you said, just like a MATLAB, there's no one way. All right. I see yesterday Professor Adediba was using ADD, okay, right, to add the things together, just so many ways, Shobola, okay. I believe there should be other ways to do that. They are not rigid. What you have there are actually not rigid, okay. So you can actually explore, Python's, okay, explore Python functions, modules further, okay. All right, but that is just one way. That is just one way of doing it. That is just one way, okay?
One more question, sir.
Yeah.
Okay. Thank you, sir, for the presentation. My name is Rachel Kemi. So you mentioned something about optimization, and you mentioned these things. So I'd like to know if there is a mathematical expression to actually convert a convex objective function to non-convex, or either ways, like maybe non-convex to convex.
Yeah, yeah, that would be Rachel. Yeah, that would be another. Maybe Adetiba will organize another one. Then I will come and talk on optimization. Really, that's a whole ball game on its own. All right, okay. So we can discuss this, okay, on another forum. All right. Yes, we can convert. Yes, very well. Okay. But that will be I hope Adetiba will call another workshop, or a forum where we can also talk about this. Okay.
Yeah, apparently, Doc, I know optimization is also called for most of the research students. So we can spin off maybe a mini school at a later time to really, really dig down into that. So it's part of what we are hoping to do. So thanks. That I think the student can also
good.
The student can also interface with you, so that we are not going outside the scope of this current class.
Yes, sir.
Exactly. So to also add the question that just to complement what you said, Julius was asking about the application of the outer product. An immediate application is when you are doing weighted input. In neural network, you are multiplying the input, which is a matrix or a vector. You are multiplying it with the weight and the bias. You do outer product in order to do that. That's an immediate application of that concept. Exactly. So just to complement the example you also cited.
Yeah, thank you. So we have norms now, norms of vectors. Like I said before, a norm is actually a way of finding the largeness of a vector. How big is the vector? The magnitude of the vector, the length or the size of the vector. The most common one, which we are all familiar with, which of course we have also been dealing with since our secondary school days, okay, is the two norm, what we call the Euclidean norm. For instance, when you say you want to find the magnitude of a vector, okay, you are actually doing the Euclidean norm. All right. Okay. In those days, I remember we used to find the magnitudes of complex numbers. Okay, we are actually doing this Euclidean norm. All right, by simply, for instance, if you have 2 plus J5, okay, 2 plus J5, you create a vector there. You know, we didn't know what we were doing those days. We just find square root of 2 square plus a 5 square. Okay, we're actually doing Euclidean norm by finding the vector that relates to that complex number first as 2, 5. V equals 2, 5. Okay, that is what it is. Okay, this is very fundamental. It's just a fundamental way of finding the length of a vector. Okay, and this is used a lot in so many applications. The machine learning, is just useful, and it is represented as this. Okay, see, norm of V is the same thing as this, 2 norm, Euclidean norm, 2 norm. It's the same thing. It's just square root. It's just the square root of the inner product of the vector by itself. Okay, you can see what we have here, V transpose V. Okay, V transpose V is actually an inner product of V by itself. The square root of it will give us the Euclidean norm. Okay, we can see. Okay, all right. An important expression is this. Okay, you see the vector itself is actually the product of its Euclidean norm and a unit vector in the same direction as the vector. You can see this is Euclidean norm. Okay, this is a unit vector. Okay, in the same direction as the vector. So it means that a typical vector, a typical vector can be reduced to a product of its norm and a unit vector, okay, in the direction of the vector. Are we together? You see, this is a unit vector, and then this is its norm. You see just one line representing a vector. Okay, you can just break that into 2. We have a unit vector in that direction, multiplying the norm, the size, okay, of the vector. The size of the vector multiplied by its unit vector is actually the vector, right? This is very important. Okay, meaning that of course you can find a unit vector. Okay, you have a vector, you can always find its unit vector. Okay, from here, some important features of a norm are these. Some important properties. Okay, number 1 is non-negativity. Okay, that is, the norm of a vector can never be negative. It can never be negative. All right. Okay, that's what we are saying, equal or greater than 0. Okay, it's either 0 or positive. And then in case it is 0, it means the vector itself is 0. That is, it's a 0 vector. All its elements are 0. For this to be so, it means all its elements are 0. That's why we call it definiteness. Okay, it's either the vector is 0 and then its norm is 0, or the vector is not 0 and then the norm can never be 0. Okay, the other one is called homogeneity. See, a scalar multiplication here. All right, it's the same thing as this. Okay, the magnitude of alpha multiplied by the norm. Okay, then the last one is the triangle inequality. Okay, add these 2 vectors together, find their norm. The result is going to give you this. Okay, it's equal or less than this. Equal or less than this. Okay. Other norms are infinity norm and then the general P norm. Okay. You can see here the infinity norm is actually telling us, the maximum absolute value. That is the maximum. Okay, the maximum absolute value. You can see it, maximum absolute value. For instance, if V is made up of -2, 3, -5. Okay, the infinity norm there is actually 5. Okay, you find the absolute value of each of each element, okay, and then compare these absolute values and then choose the one that is the highest. Okay, that is the infinity norm. Okay, and then we have this general P norm. You can see V P norm, right? Look at the difference between. You see the difference? Look at these two norm. Okay, you can see that this is a VI squared raised to power 1 over 2. This square root is 1 over 2. Okay, VI squared raised to power 1 over 2. That is the 2 norm. Then P norm will now be P squared, root square, okay, of this raised to power P. That is what we have here. Look at this. Okay, 1 over P, see P norm, absolute value of VI raised to power P, then everything raised to power 1 over P. Okay, it's similar to the 2 norm. If P is 2 now, then it becomes the 2 norm or the Euclidean norm if P is 2. If P is 5, okay, if P is 10, all right, okay, but you notice as you are increasing P here, the result will be tending to this infinity norm. The result will be tending to this infinity norm, okay? Increase P further and further, the result will eventually tend to the infinity norm, okay? So, the result is between the 1 norm and then the infinity norm. Okay, when you increase gradually from 1 norm to the infinity norm, okay, you are going to get a value that does not depart from this value here. That is when you increase from 1 to P, okay, right? That is 1 to 2 to 3 to 4 to 10 to 20 to 50 to 100. As you are increasing, you are tending to this infinity norm. Okay, yeah. And then we also have a code there, a Python program there. Okay, we can see this, right? The first one is the Euclidean norm. Yeah, after you have defined your array, okay, we have the normal norm. You see, norm of V, that is the Euclidean norm. Okay, the next one is okay, the 5 norm. You can see I'm using ORD, that is the order is 5 here. D comma ORD 5. Okay, you can try 10, you can try 20.
Okay, Dr. Oshin, you can moderate the interaction. I'm thinking he just touched on the infinite norm. Can anybody tell us what he or she thinks this is all about? And he has provided the mathematical representation. So who can elaborate on it? And maybe what you think the practical relevance could be, at least to see if we are flowing with what he's teaching us.
All right. So do we have reactions to his presentation so far?
Good morning, everyone. My question is the properties for the norm that was given. I want to ask if the properties apply to the general P norm, or is it just the 2 norm?
Dr. Awelewa?
Can you hear me?
Okay, yes, we can hear you now. Did you hear the question? Yes. So if someone has, a response to what he asked, we can say something or.
Based on my understanding, I think it's actually applicable to everything. If you look at based on the explanation he gave to us, for instance, he said we have the Euclidean norm, which is the 2 norm. Then we have the P norm when the parameter varies. And he also says something that when P tends towards infinity, then it becomes an infinite norm. So that shows that there is a relationship between them, depending on the P value that you're choosing. may pick your key to be 2, pick it to be 3, pick it to be 4. That is why in that Python code, you have your P, you have the order there specified there. You have the conventional one, which has just the V value, the V, that's your norm, the norm of the vector you want to find. Then the remaining ones, or let's say in general, you can just use, although I've not tried this, probably there may be an option like you use polarity equals to 0, or use polarity to be equals to 0. Maybe there's an option like that. Then from that shows that you can vary the parameter of that polarity, which can be 5, 6, 7, 8, or infinite. So since there's a relationship between them, then I think there's you can the properties there actually is a big.
Okay, I'm back.
So that's my conclusion about that. Thank you.
Okay, you have a follow-up.
Okay, thank you, Dr. Awelewa.
The reason I asked is that from the property, the second one says that if you have the norm of the so u, if you have that equals to 0, it can only happen if u is equals to 0. That is, the whole element in that vector is 0. However, if you are using that general p norm, if p equals to 3, you can have negative elements in the vector u. And if you raise 3, like if you raise any negative element equals to 3, you'll still have those negative elements. And then if you go on with the additions, there are possibilities that you'll have 0.
Okay. Udeme, I think it was Udeme asking that question.
It's absolute value of VI, not VI, actually.
Exactly. Absolute,
okay,
yes.
It's absolute value. All right. If you see the, okay, sorry if I made a mistake, if I didn't include that in the 2 norm. Normally we assume because it's raised to power 2, at times we don't put that, you know, but you can see the other P that included that absolute value there. Okay. All right, please take note of that. It's absolute value of VI raised to power 2. Okay.
Okay. Sorry, I want to also mention, I think that was that Udeme? Udeme?
Harry.
That was
Harry.
who? Okay, Dari. What is the value of P for Euclidean norm? So that means the P is just generalizing the norms. So
yeah,
whatever applies to P equal to 2 in the general properties will be applicable to when P is equal to any value.
Yes, that's correct.
Yeah, so that's simple. Yeah. Okay, so just to add my voice to that.
Thank you, Prof. But if you look at this now, if you look at this, can you say this? Okay, when this, you know, you see P in V infinity, you can see the answer. Infinity norm is 5. Okay, all right. If you look at this vector, you see this vector. You can see the vector that the maximum number here is actually 5. Okay. You can see it's 5. So we expect that the infinity norm will be 5. That is exactly what we have here. Okay. But when you Euclidean norm, look at the Euclidean norm, it's 5.477 something. Okay. When you see 5 norm, can you see 5 norm is 0.01 here? All right. Okay. It's tending to this. Okay. It has moved from 2 norm. You see 2 norm 5.477, okay, to 5 norm now. It's now 5.01. You see, it's tending towards. Let's change the order now. Let's change this order to like 10 and see what happens. If you change it to like 10, so it becomes the 10 norm now. Okay, it becomes the 10 norm. So I can, okay, I can now say 10. Okay, change 10 right there. All right, so if you run this, can you see what we have now? See, the 2 norm is 5.477. You can see 10 norm now. It's tending towards 5. the infinity, okay? The infinity norm. If you try 20, it's tending onto infinity, and it's going to give you 5.0. Okay, all right. So that is just it. It's just to find the length. Whether you increase P to anything, okay, you keep increasing, it's going to tend to the maximum absolute value, okay, of the element of V. Okay, and then in whatever applications you are doing, you may actually want to check and see the length. You use various lengths. I normally do this in some of the algorithms I develop. I just vary and see what happens to be able to gain a deeper insight into what I'm doing. For instance, if somebody is saying that use a 2 norm, that is use 2 norm, I want to check, okay, why not the other way around? Okay, what if this happen? What is going to happen? For instance, here, you see their norm is 5.77. Okay, it's different from the infinity norm, which is 5.0. Okay, so if I use include their norm, what is the result going to be like? Infinity norm, or for instance, if I use 5 norm, 3 norm, all right, what are the results going to look like? Okay, all right, it's a good way of playing around to see how algorithms behave. Just tweak number, change numbers around, move things around, so that you can know how these things actually work. Okay, so that is for vector norms. Let me go back to.
We have one more question, sir. Thank you, sir.
Thanks. Go ahead.
Thank you, sir, for the interactive discussion and the presentation, sir.
Who is that? Shobola?
Yes, sir.
Okay, good.
It seems every time we actually run or do this calculation of norm, anytime it's tending towards infinity, that means we'll get to be approaching the real number itself. Like in this case, from 5.47, it increases to 5.000 at 10, then at infinite, we'll get 5.0. So is there a way we can know the exact value? Okay. Another question, another question I want to ask there is, what is the...
Okay, you have gotten that, right?
Yes, sir.
Okay, good.
Why are we changing the P? Why do we have to use a particular P norm? Like when P equals to 2, why do you have to find the norm for P equals to 2, P equals to 6, or P equals to 10? Since we can easily just find, or what's the interpretation of that? Why do I have to find P at 10? Since I know that the infinite one will always give me the whole number that I want, which I can use to do my calculations or use for subsequent calculations in my work.
No, yeah, thank you, Shobola. You know, it actually boils down to the applications. Really, it boils down to the application. And then the idea is you can see that, P norm, that 2 norm, 5.4, okay, 7, and then you can see the infinity norm, okay, all right? In some applications, you will discover that whether you use a 2 norm or you use even P norm, your results are not going to be affected. The errors can be tolerated. Okay, so you have no problem. All right, but in other applications, you have to know the right length of your vector, the right length of the vector that will suit your the application. Okay, like I said before, it's the 2 norm that is commonly used, but you can also try. You can try the other ones and see the error margins. And that is what I said before. You can compare things. You are not limited. You want to know the performance level. You want to know the error margin. If you use something different, that is the way we do research. It's not rigid. But one thing is they are used to find the length, the magnitude of vector, the strength. What is the strength of this signal? We want to know the strength of the signal. One way to do that is to compute the norm. Okay, so it depends on the applications, Shobola, and that is why I encourage you to try some of these things out. Don't just accept what authors, article authors are telling you. Okay, try to replicate what they do and move things around. varied numbers, very change algorithm to you and see what is going to happen. By that, you learn a lot. In fact, I normally encourage students to replicate very good research articles. See how you can replicate them. If you can replicate them, oh, that is the step one, okay, to advancing research in that field. All right, you have what experts have done before, especially a renowned expert, and you pick up an article of theirs, and then you replicate it. I assure you, you have actually covered miles. And how do you replicate this? You just change things around, and then you get a deeper understanding to what is happening. So it depends on the application of Shobola, but what I'm trying to say is, okay, it doesn't exceed the infinity norm. Okay, it doesn't exceed. You can see the error margin between the two norm and the infinity norm. Okay, this can be tolerated in some cases it cannot be tolerated. You just have to use the right one. Okay, the right length of the signal you are dealing with. That is vector signal you are dealing with. Thank you. Can I proceed? Cover some of them. So the next one is linear combination, dependence and independence of vectors. Okay. This is very good. This is very, very important. Very important. For instance, you have looked at an image and then you have converted the image, okay, into a matrix of pixel values. All right. And all of these are arranged, okay, in row column manner. Row column manner. Okay. You want to check, one of the things you want to check is whether these columns or these rows are related. You want to check that. When you say related, are they dependent? Okay, are they dependent? If you are having columns that are dependent, that is, you can find one from the other. Why do you have to include that in that set? Okay, you may have to look at ways to reduce that matrix further. Okay, so this is a very good application in that area. You want to find the linear dependence and independence of vectors. Okay, that is what I want to talk about now. So given a set of vectors V, given a set of vector V, can you see V1, V2, Vm? I want you to pay attention here now. This is V now. This is now a set of vectors. V1 is a vector now. V2 is a vector. Vm is a vector, and that is why you are seeing this Vi. Vi is an element of an n-dimensional space. Okay, thank you.
I think you can move faster now since the foundation seems to be properly laid.
Okay. Okay, Prof. Thanks. So here now, linear combination. We have a set of vectors. So we can see V1, V2, Vm are actually vectors in this set, just this set. Okay. Now, but we know each of these vectors is an element from an n-dimensional space. Okay. So we say that a vector Z now is a linear combination of these elements. Okay. That is, we combine this element to produce a new Z. Okay. Yeah, that is what we have. That is what we have here. Look at it. Look at it. Okay. It's a linear combination. If this exists, you see Z equals to alpha I Vi. Can we see we have non-zero alpha highs such that this exists? All right, so we say this Z is a linear combination of this V1 and V2, okay, together. All right, if you can add V1 and V2 together and then we obtain a new vector, then that vector is a linear combination, okay, of these vectors, right? Another vector, we can just add 3 elements together. That will give us a new vector. That is a linear combination. That is what we call a linear combination. Okay, and then you can add the matrix that represents your system. Okay, if 2 columns of that matrix, okay, can be, all right, are related such that one can be obtained from the other. Okay, it means that, you know, the column vectors of the matrix are actually not independent, because a coulomb can be obtained from right, by combining the other coulombs. Okay, so this is just a linear combination. We say it's a linear combinations. When we multiply the elements of this and then we add them together, we have another vector. So it's a linear combination. Good. Okay, so we talk about linear dependence now. We talk about linear dependence as follows. If again this vectors V, okay, it is possible to have alpha I. In this case, it is possible to have alpha I such that these holds, okay, such that these holds. Then we say this V, okay, these vectors are linearly dependent. Okay, you can see Vj here, that is, we can obtain one from this set. We can obtain a vector from this set as a linear combination of the other ones. We can see, I want us to pay attention here. We see, okay, this is alpha I, Vi, okay, from I to M, all right? Because we have M vectors. So from I to M, so we have alpha, for instance, 1, V1 plus alpha 2, V2, etc. Okay, and you can see this caveat here, I is not equal to J, because we are trying to find Vj now. Okay, for instance, if you are finding V1, if it is V1 that is a linear combination of the other, it means that, of course, you won't take in I equals to 1 here. That is the implication. So if this holds such that alpha i's, or at least one alpha I, is non-zero, then Vj is a linear combination of all of these. So it means that this vector V, this V is actually not linearly independent. That is, they are linearly dependent. This is very, very important. Okay, this is very, very important. You have a set of vectors, okay, and you want to check if these vectors are linearly dependent or linearly independent. Okay, if the vectors are linearly dependent, it means you can obtain one of the vectors by combining linearly the other vectors. Okay, if the vectors are linearly independent, it means that there is no way you can find a vector from this set by combining the other vectors together. Okay, that is a simple way to look at this, right? Okay. So how do we actually check whether the vectors are linearly dependent or linearly independent? How do we check? Okay. One way to, I put the derivations initially, but I just removed the derivations really. Okay. All right. So one way to do this is actually to stack these vectors together to form a matrix and then find the determinant of the matrix. If the determinant of the matrix, okay, is 0, it means that the vectors are actually linearly dependent. The vectors are linearly dependent. You can see determinant of V1, V2 up to Vn. If you find it, if the determinant is 0, definitely your vectors are linearly dependent. You can find at least one of the vectors, okay, by combining the others. Okay, by combining the other. It means you're actually repeating features. You are repeating features now. You have to pay attention. Okay, you are repeating features, really. For instance, why do you have to combine, why do you have to combine, okay, you have Shobola, you have Udeme, you have Dari, okay, all right, 3 of them, all right, instead of having, for instance, okay, yes, this unique set, Shobola, Dari, Udeme, and then you are having Shobola, Dari. Okay, all right, then something is wrong with that combination. All right, you're not going to have an optimal performance in that case. Okay, because you are just having that twice. And Shobola, do you think you have three team members? Okay, there is a particular contribution that should come from Udemy that none of these team members can offer. Okay, so you have to prune the system. Okay, all right, that is just the analogy here. Okay, so don't forget the way to check this is to stack this together, concatenate these vectors, all right, and then find their determinant. If the determinant is 0, then the vectors are linearly dependent. If the determinant is non-zero, then the vectors are non-linearly dependent. Okay, that is exactly so. Linear independent, that is exactly the way to handle it. Okay, see, stack them together and then you check. Okay, all right, so it's the same thing I'm trying to pass across here. So linear vector spaces. Out of this very large space, we can also create a subspace. It's also possible to create a subspace from the general space now, vector space. Okay, and this subspace has its own features too. Okay, and these features are also the same as the features of the original vector space, addition and scalar multiplication. Every subspace from this vector space, original vector space, must actually obey addition and scalar multiplication property. Okay, so here, if you consider two vectors UV, okay, from S is now a subspace. S is a subspace of this general n-dimensional space, okay? And then we have this scalar alpha, then S is a subspace if these two conditions hold, these two equations hold. That is, we can add two vectors in the space, and the result will give us a vector that is also in the space. Okay, if you multiply a vector in the subspace by a scalar alpha, we also get a vector that is also resident in the subspace. Okay, so actually vector spaces they are just as they are called, the subspaces of the original spaces, but they still preserve some of the characteristics of the original space. Okay, and as you have seen, addition and scalar multiplication property, okay, which is a property that also characterizes the original vector space. Okay, we talk about a span. Here. We are saying if a subspace represents all linear combinations of a given set of vectors, we have these vectors, okay, and then we have a subspace, all right, that represent all linear combinations of these. This is what I mean. From this set of vectors, we can create actually a subspace by combining this in so many ways. We can combine V1, V2, Vm in so many ways. For instance, I can add all of these vectors together to get a new vector. Okay, that will be an element of the subspace. I can add just V1 and V2. That will be an element of the subspace. I can add this and this and subtract it from this. That will be an element. Okay. So what I'm saying is we can form all linear combinations, carry out all linear combinations of this. Okay. All right. These linear combinations represent, okay, we actually form a subspace. All right. We form a subspace. Okay. So we say that the subspace is spanned. Okay. Is spanned by these vectors. That is just it. If we are using this to create a subspace, then we are saying that the subspace is spanned by, okay, that is spanning, you know, it spans, okay, all right, it spans this range. That is, we are using this range of vectors to form a subspace. If that is the case, the subspace is actually spanned by this set of vectors, okay? And then we say we represent it by this, span of this. So when we say span of this, we're actually talking about all linear combinations of this. And these linear combinations actually represent a subspace that is span. Okay, then we'll move a step further to say, oh, okay, let's look at these vectors actually very well. Are they linearly dependent? Are they linearly independent? Okay, if they are linearly independent, then we say that the subspace is actually a basis. Okay, we call it a basis. If the vectors are linearly independent, that these vectors are actually unique. They are all unique. If they are all unique, it means that when you combine them together, you are actually going to get something different. The linear combinations are actually different. When you combine them together, you are not repeating anything. And that you say is a basis now. It's now a basis for the subspace. Because when you combine the basis element, combine all of them together, you are going to get a unique subspace. Okay? Space is the number of vectors. Basis, okay, actually represent these vectors. Okay, they're also called basis vectors, and each element is also called a basis vector. Okay, a basis vector. So we have natural standard basis, natural standard basis. For instance, look at this. Look at this. Okay, this linearly independent vectors E1 1 0 up to 0, E2 0 1 up to 0, and then 0 0 up to 1. I know if you look at these are very familiar. Okay, for instance, if n is 3, if n is 3, E1 is 1 0 0, E2 is 0 1 0, E3 will now be 0 0 1. Okay, that is like an identity matrix if you stack all of them together. Are you with me? If you look at this vector, you see that they are linearly independent. If you look at them, they are linearly independent. You can't get one from the other. There is nothing you can do to get E1 from combining the rest. Okay, that is why we say they are linearly independent. So we call them natural bases. Okay, so if E1 is 0 1 0 1 0 0, okay, E2 is 0 1 0, E3 is 0 0 1. Okay, it means that we can create all set of three-dimensional vectors by just combining these three natural bases. Okay. Just think of any 3 by 3. You can always create them from this natural basis. Okay, so when you know the natural basis of a subspace, okay, you can actually look at this natural basis and understand what they represent, understand what they connote, and then you can take that to the other vectors. You simply move these same characteristics, you generalize over to the other vectors. So this is very, very good. If you have the understanding of the standard basis or the natural basis, okay, it's as good as having access to this subspace. A subspace and its basis always go together. A subspace and its basis. The basis is used to create the subspace. The basis is used to create the subspace. Okay, all right? If you understand the basis, then you can create the subspace. That's what we are saying here. Understand the basis, then you create the subspace. This is extremely useful, extremely important, okay? Don't forget the concept here, linear independence and linear independence. Linear independence and linear independence. If you have a set of vectors, and you can find at least one of them from the others, then these vectors are not linearly independent. They are not. Futures are repeated here, like I said. Okay, we have to look at how to better manage the the situation. We go a step further. We go a step further. If these basis vectors, we say that basis vectors from the span now, okay, we have the vectors that we use to create the subspace. We call these vectors the span, okay? We say if these vectors are actually linearly independent, okay, we say they represent a basis, okay? Now, in addition to being linearly independent, if these basis vectors are mutually orthogonal, okay, we call the basis orthogonal basis. We say they are called orthogonal basis. When we say orthogonal, what are we trying to say? Orthogonal, what do we mean? Look at this V. V equals to V1, V2 to Vm, okay? A set of vectors, all right? Of course, we can create a subspace from this set of vectors. Okay, so if this set of vectors is actually linearly independent, so they become this basis for the subspace we create. Okay, and then again, if this set of vectors, okay, is orthogonal, okay, orthogonal, then we say that they constitute an orthogonal basis. So when we say two vectors are orthogonal, this is what we mean. This is what we mean. I know in your articles, you see this a lot. Keep talking about orthogonal vectors, orthogonal basis. You get to see some of this in scientific articles, okay? So when we say two vectors are orthogonal, this is what we mean. You can see this symbol again, okay? The inner product, see the inner product, all right? It means that when you find the inner product of two of these vectors, okay, you are going to get 0. You see, you are getting 0 here, right? So it means that the vectors are mutually orthogonal, okay? Are we following? All right? So we say the basis is actually an orthogonal basis, okay? Again, we move a step further. If the basis vector, in addition to being orthogonal, now have unit norms, okay, then we say that this basis set is also an, okay, orthonormal basis, okay. When we say it is orthonormal, this is what we are trying to say. Again, V equals V1, V2, Vm, okay. Then the norm of each of these is actually 1. That is, they have unit norms, you see. 1 for I equals to 1 to m. All right? Are we together? Remember, orthogonality is when you find the inner product of two vectors and you get 0. It means the two vectors are orthogonal. Okay? When you observe further that the norm, Euclidean norm of each of the vectors is also 1, okay, then they are orthonormal. They are orthonormal, okay? And if you have a basis vector like that, then we say that, okay, it is an orthonormal basis. Orthonormal basis. Okay.
Hello, Doc.
Yes, Prof.
Is that an Euclidean norm?
Yes. Yes.
If it is Euclidean, okay, yeah, it is. Okay. With that symbol.
Yeah.
Okay, yeah.
Yeah.
Okay.
Yeah, it's if it is 1.
Yeah.
Okay.
Somebody
okay.
posted I think in order for the audience to also flow along with you,
yeah,
is also trying to expatiate on orthogonality, what it thinks it means. Maybe you want to pick it.
Can it?
Michael Anthony is saying that right angle to each other. So he's trying to also elaborate on what is meant by orthogonality.
Yeah. Who is that?
That's Michael Anthony.
Yes,
so I think
yes. No, it's correct. No, it's correct, Prof.
It's actually correct. I just wanted you to pick that and also.
Okay, thank you.
That others
okay.
I know it's very correct. Yeah, thank you.
Yeah, it's the cosine. It's the cosine of the angle between the two. Yes, which is going to be 0.
Maybe I should mention here that you can you remember I had to use this concept in my PhD then.
Cosine distance.
Cosine distance in order to determine if mutations in genes if there's mutations in gene or there's no mutation by comparing a non-mutated gene with other types of sequences using the concept of orthogonal basis or cosine distance. So these are ways these concepts are applied, whether you are in bioinformatics or you are doing genomic signal processing, another aspect of signal processing. So I just want to mention that.
Yeah, thank you, Pro. I recollect that time that you had to find your way around all of these things. And then, and then you got it right, which is good. Yeah, they are very good. I just hope those who are listening to us today will actually explore this further. Okay, like I said before, really at a glance, some of these things are not they are not appealing. Okay, so we also felt like that at times. We felt like that when we started. These things would like push you away. What are these? These mathematical concepts are difficult to comprehend. No, they are good. So when you keep at it, so you are going to break it, and then you find out later that very useful, very useful, very useful. I also recollect that Dr. Badejo, that time too, was also trying to find a way around all of this, reading algorithms, trying to break algorithms, all of these algorithms. I'm talking about image processing algorithms now. That time, we discussed a number of these. We tried to work around some of these things then. Okay, but what I'm saying is they are very, very good. Don't be pushed away. Don't be pushed away. I said initially, you need to explore this further. Don't just stop. Explore, don't be discouraged. Explore them further. And then we are actually open. If there is anyone that needs further elucidation after this, of course, you can contact us. You can contact us. Really, actually, this is fundamental. All right. We can take it to the next level. Thank you, Professor Adetiba.
Thanks, Doc.
Okay, the next one is row space. Okay, row space. We have discussed vector space now, all right, subspace now. Okay, if you have a matrix, all right, you can also create a row space from the matrix. Okay, by simply using the rows. You use the rows of the matrix to create another row space. Okay, you just add these rows of the matrix, combine all of them, do linear combinations of them, and then you have what we call a row space. Similarly, you take the coulombs of the matrix, combine them in so many ways. You can add all of them together. You have a vector. You can add two vectors there, and then subtract that result from the other, and then you have another vector. So you can create also a subspace by using the rows and then the coulombs of a matrix. Okay, when you use the rows, then we call it row space. When you use the coulomb, then we call it a coulomb space. Okay. Okay, we'll come back to this later. All right. We also talk about a null space again. Null space. All right, from a vector space to subspace to row space to coulomb space, and then to null space. Okay. Anytime you have a matrix that this equation holds, okay, that you can find a vector, okay, such that the matrix multiplied by the vector, you're always going to get 0, then A has a coulomb null space. And it means that this vector actually belongs to that null space. Okay, for instance, we have a matrix A. We have a matrix A. If the inverse of the matrix exists, it means actually that the null space does not exist. Okay, it is when the inverse of a matrix does not exist, the determinant of a matrix does not exist. Okay, for instance, we remember the system of linear equations, AS equals to B, AX equals to B. Okay, if the inverse of A exists, we'll always find a result. We'll always find X. Okay, we'll always find X. But if the inverse does not exist, it becomes difficult to find. So it means in that space that A has a null space. It has a null space. Okay, we can find a vector such that when we multiply and the vector together, we're always going to get 0. That's what that is telling us. We can do that for the row too. See where we are multiplying it. It's PA now. It's left, okay? We also say left null space or row null space, okay? Here is column, or we call it right null space, okay? These things are quite good. Linear transformation, okay? The background to this is actually matrices, okay? So I discuss some important matrix background here, okay? I say that a matrix is a rectangular array of similar objects or things, which I have mentioned before. So this is a matrix. A equals to this. It has m rows and n columns. The number of rows is m, and the number of columns, okay, is n. So we can see them. That is a matrix. I'm saying here that the ith row is the n vector. I want you to pay attention here. The ith row. For instance, row 1. How many elements are in row 1? N. You can see n. Row 2, n. Row m, n. Okay, so each row is an n vector. Okay, each row is an n vector. The number of rows is m. Okay, but each row is an n vector. That is, each row is an n-dimensional vector. N-dimensional vector that comes from a set of all n-dimensional vectors. Okay, this is what we see here. Okay, the ith row is an n vector, and this is what it is. Look at it. AI full column. I want us to pay attention to this notation. AI full column. Okay, that is, I is the row. This column represents okay, the column now. Okay, the columns of the matrix. If you are at row 1, all the columns. Row 1, all the columns. Row I, all the columns. Are we together? So this is the way to represent that. Look at this. This is row 1, A1 column. So you can represent all of this by just one vector. Okay, row vector A1 column. Like what we have here, AI column. Okay, you see the representation here. I also need you to pay attention. You see the representation. Okay, if you transpose this, look at this, you are going to get AI1, AI2, up to AIN in a row fashion. I just wanted to present this like, okay, in tandem with the normal column, okay, column presentation, or column-based representation. That is why I put it this way. It's still the same row vector, AI column. So it's AI1, AI2, AIN in a row fashion or in an horizontal fashion. Okay. All right. And then you can see it's an n-dimensional. Okay. It's an n-dimensional vector because the number of entries or elements is actually n. Okay. This applies to all the rows. You can also see it's from I equals to 1 to m. All right. That's some of the things you see. You'll be wondering from I equals to m. And then n, yes, don't get confused. Just the number of rows is m, but each row is actually an n vector now. Similarly, the jth column is the m vector, okay? The jth column is the m vector. Let's look at this column, okay? How many elements do we have? M, 1, 2, up to m, okay? So that is what we have here. All right, all the rows and then the J. You can see all the rows and then the J. Again, look at it. This is column 1. Okay, so column 2. Okay, this is column 2. You can see this is constant. 2, 2 down. But the rows change, 1, 2 up to M. Okay, so you see, unlike the rows, see the rows, row 1, you can see the index, the row index 1 remains the same, but look at the Coulomb index, it changes from 1 to N. Okay, so that is it. So for the Coulomb, you can see it's an M-dimensional vector because the number of elements or entries in the vector is M. Okay, even though the number of coulombs is actually N. Okay, good. All right, so this matrix again can be written in terms of its rows and coulombs as follows. I want us to pay attention. Okay, you may not have seen this before. You have seen, you know how to, okay, how to interpret matrices in terms of number of rows and coulombs. Okay, but this may be quite strange, right? But it's not something difficult to grasp. We are simply saying that represent the first Coulomb by a vector. Represent the second Coulomb by a vector. Represent all the Coulombs by a vector. That's what we are saying here. Okay, so this is Coulomb 1. This is the way we represent it. You can see it. All rows changing, but Coulomb fixed, Coulomb 1. This means that the rows are changing. Similarly here, Coulomb 2, the rows are changing. Okay, that is for that. We can also represent that in terms of the rows. Look at the way we represent the first row, A1, okay, the Coulomb, all right? That is row 1, Coulomb, the coulombs, row 2, all the coulombs, etc. Okay, at times we also represent the matrix like this, right? Okay, or like this, if there is no dimensionality ambiguity. Okay, all right, important properties. Okay, again, important properties which are useful in linear transformation. Okay, again, we do transposition, right? If you have a matrix this, M by N, okay, that is defined as this, which is the same thing as this, then we can find the transpose of A. Again, I want us to pay attention here. Look at what we are doing. You know, if you have normal row vector, for instance, 1, 2, 3, normal row 1, 2, 3, and then you want to find the transpose of that, you just flip from horizontal to vertical direction. That's it. Very easy to do. But look at this. Okay, the elements here are not scalars. Okay, so if you want to find the transpose of this, you actually have to transpose the entire, and then you now transpose the elements, because the elements are actually vectors now, they are not scalars. So look at what I've done here. Can you see? For the first one, okay, I shifted this, I shifted it vertically, okay, from horizontal to the vertical direction first, and then I now transpose each vector element. And now transpose each vector element, you can see this transpose, transpose, transpose. Similarly, this, okay, if you are representing the matrix as an element, represent its element as vector elements, okay, right? You just do the same thing, shift this horizontally, and then you transpose each element. Again, you will come across, you also come across some of these things while reading scientific papers. In scientific papers, you won't see where they are moving numbers, scalars around for you. They say this is 1 times 2 times 3, add them together. No, they won't do that. They actually represent things in a more compact and efficient manner. More compact and efficient manner. And that is one of the attributes of vector matrix representations. You see, things are neat. Things are neat, but because they are neat doesn't mean that if you really don't have the understanding of what is happening, you may not be able to comprehend. So this is, this is a good way to actually represent matrices. I want you to note that when you multiply matrices together like this and then you transpose the result, you also have this. It's also the same thing. Okay, in case you come across this while reading paper, all right? And if you want to check this, you can use simple matrices, like, like two by two matrices, okay, to confirm this. Okay, I just had to ship that in because when you are transposing, you have to bear this in mind, right? Again, you can add and subtract as before. You can do scalar multiplication, okay? So you can follow these things. Then you can do vector matrix multiplication. Vector matrix multiplication. I know you are familiar with how to multiply, matrices together, multiply a matrix and a vector, okay, in a number by number fashion. All right. But now, this is a new way. Of course, it may not be new to you, but I think this is not common, but it's good for you to actually understand in case you come across this in papers. So if you consider A to be an m by n matrix, and then U is an element from this n-dimensional space, and V is also an element from this m-dimensional space. Okay. A multiplied by U is going to give us this. A multiplied by U. All right. First and foremost, I want you to see that m by n multiplied by m by 1. This is like m by 1. So if you multiply m by n with m by 1, you are going to have, okay, you are going to have, n by 1. You are going to have m by 1. Okay. All right. This is actually, this matrix product, okay, is actually conformable. So to multiply this, look at the trick. This is one trick. Okay. We take this representation. Look at it. Okay. All right. This representation. That is what we are using here. And then we now multiply it by uj. Okay, uj is actually an entry of u. Remember, u is a vector now. U is just a vector. Okay, A is a matrix, but we have represented A now as a block matrix, so to say. Its elements are now vector elements. Again, I go back. This is what we are using now to perform this matrix vector multiplication. So we are multiplying U now, this and U together. So it's like we are multiplying element of U by this, and adding the result. I hope we can see this. Okay, this is what we have here. For instance, if J is 1, it means U1. That is the first element of U. You can see it. Then multiply by, okay, multiply by A coulomb 1. All right. That is the first, let me show you the first coulomb from A. Show you again. First coulomb from A. Okay, which is this. Then multiplied by the first element of U, have the result. Add it to the next when J is 2. Okay, the second element of U. All right, and then this second coulomb of A. You multiply this and add all of them together. That will give you this product. That will give you this product. Okay, we can also multiply. We can also multiply a row vector and a matrix. Okay, A is an m by n here, right? And then V is m by 1. But in order to be able to multiply V and A together, for instance, if you look at this, 8 times V are not conformable for multiplication. Okay, if you look at this, they are not. All right. Okay, so if we do this, this is m by 1. Okay, and then we transpose it, it becomes 1 by m. All right, 1 by m. So we have A to be m by n, so we can multiply the two together. So 1 by m and m by n are multiplying. So the result is going to be 1 by n. But again, look at the approach. we are multiplying each element of V, okay, by, look at this representation, okay? This is the representation we are using now, all right? So if you multiply this together and then add, multiply and add, we are going to get, okay, this, we are going to get the result. All right, so you can multiply any matrix and a vector as long as the product is conformable for multiplication in this manner, okay, in this manner, in a compact form. And then we also do matrix multiplication in this same compact form, all right? If A is an M by N matrix and then B is an N by P matrix, then we can find the matrix C, which is a product of A and B. And you can see they are conformable for multiplication. You can see them M by N multiplied by N by P. So the result is going to be M by P. Okay, it's going to be M by P. So we can find each element of C. We can find each element of C as follows. Okay, Cij is going to give you an inner product of AI, okay, Coulomb, and then B Coulomb J. Okay, so this is going to give you that element Cj, and that should not be also difficult to understand because we are saying, okay, Cij, we are saying that the ith row from A multiplied by the jth Coulomb from B. That's what we are saying. Okay, here, if you want to find any element here of C, just any element, and you don't have to perform the entire multiplication before you know the element, you can just straight away to find any element. For instance, C12, to find C12, just do the inner product of the first row, okay, and the second Coulomb. That will give you Cij. You can do that, okay, and in fact, you can even write a Python function that will just do that multiplication for you. And I encourage you to, okay, to do this just by using this basic algorithm, all right? So you can multiply any two real matrices together. This is another way to also do this, okay? This is another way, Cij, which of course is the same thing as this, okay? This is actually expanding this. This is yet another way to do the multiplication. You see, I have represented A, okay, in this fashion, in a Coulomb fashion, where each entry is a row vector. A1 Coulomb is a row vector, A2 Coulomb is a row vector, as I described before. All right, and then element B, a matrix B, okay, I have represented also in this fashion, in a Coulomb fashion. The first Coulomb of B, second Coulomb of B, okay, up to the last one. So you can multiply this easily. This times this, 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 etc. This is also another way to find the multiplication of A and B, as long as the product AB is conformable for multiplication. Okay. Then linear transformation by a matrix. Linear transformation by a matrix. If you have a matrix A, which is M by N, and then we have a vector U, which is N by 1, okay? We can multiply A and U together like this, and then we are going to get a new vector, which is M by 1. You can see the dimension of the new vector. It has changed. You can see that. We have this vector U and then we have this A. Multiplying this together is going to give us a new vector whose dimension has actually changed now. Okay, if M is less than actually N, then you have reduced the original dimension. Okay, if also M is greater, then you have increased the dimension of the original vector. Okay, this is what we call linear transformation. We are just transforming one vector, okay, from one space to another space by using a matrix. Okay, We are using a matrix. So this is very important. You can see the representation. We are using a matrix to actually move vectors from one space to the other. Here, in this case, from n-dimensional space to m-dimensional space. Okay. This is core to linear transformation generally. Very core to linear transformation. It's also very important to dimensionality reduction in many of the application areas where this is useful. Okay, it's very, very core to it. Okay, some person may have some ideas to also share in this area.
We have a couple of questions on the chat section.
Okay.
Okay. So Julius Odunuga said, what happens if the resulting matrix after stacking the vectors is non-square, as non-square matrices do not have determinants?
Yeah, which stacking
the vectors. What happens if the resulting matrix? So I think this was asked.
Very good. That's a very good question. Yes, if that does not, yeah, I rush, because of time. Very good. Julius, right? You said Julius.
Yes, sir. Good.
So good that that question has taken me back to that. Right. You see this? This study. Okay. All right. This is when m is equals to n, when it is square. Okay. If it is not a square, then you have to do this. You form a system of linear equations. Okay. And then check this. All right. I'm going to check this. If the only solution to this is when these alpha i's are all 0. Okay. Then the vectors are linearly independent. Okay, but if you can find a non-zero alpha I from here, a non-zero alpha I, then it is linearly independent. That is the set, that vector set is linearly independent. So that is the situation, okay? The other one is this, when m is greater than n, okay? All right, of course, this is quite trivial. You know that, of course, the vectors are not linearly independent. All right, for instance, if you have the first column made up of 2 elements, the second column made up of 2 elements, you have another third made up of 2 elements, fourth made up of 2 elements. Of course, you can see in that case that the vectors can't be linearly independent. This is the situation, okay? All right, this is when you can apply that concept and determinant. Okay, thank you, Julius.
Okay. So another question says, during the presentation, you talked about someone who built his own machine learning algorithm due to the unavailability of suitable algorithms for his problem. For those who want to implement their own ML algorithms, apart from understanding linear algebra in general, what are the other necessary knowledge to have? Right? Are there some recommended platforms to help you build your own ML algorithm?
Yeah, no, what I was saying was that, of course, there are existing algorithms, and these are big algorithms, very common that we use, okay? All right, I'm not talking about those ones really. I'm talking about a situation where you need maybe some functions and they don't exist in Python, they don't exist in MATLAB, they are not there. I've seen cases where students were struggling. They were just struggling looking for a particular function that will solve their problem. They went to MATLAB Central and they didn't have any solution. They went to other platform, they didn't see, okay? All right? Until they had to contact somebody who wrote that, that for them. All right, so that's what I'm trying to say. For instance, if you are using Python, okay, and then you want to write a function in Python to solve a particular problem, and you really don't have this function available, okay, or you can't get it elsewhere. Yeah, so it means that you actually have to sit down, right, and write it yourself. And then the first step is to actually understand the algorithm. You have to understand what you want to solve, okay, before you can actually translate them into very useful code. Okay, so you need the requisite knowledge to be able to do this. That's what I was trying to say. Apart from this, of course, you also need the domain knowledge, really. All right, you also need the domain knowledge. For instance, if you are in chemical, if you are in the biological sciences, okay, there are attributes of a biological concept you can take advantage of, okay, to also write the same program. All right, so the domain knowledge is also very, very essential. All right, apart from this, the domain knowledge is very essential. Thank you.
Yes, sir.
I just want to lend my voice to, in addition to what Dr. Awelewa has said, the question by these students, that is the only linear algebra that is needed. If you look at the timetable for this boot camp, you will see that we also have calculus, the differential equations, which is then chain rule. When you are doing backpropagation, you are doing gradient descent. But the concept of gradient descent is actually drawn from a chain rule. Chain rule comes from calculus, which is differential. Of course, differential equation is a component of calculus. Okay.
Yeah.
So it's not just linear algebra that you need, and that's why we have. By the next phase of this part 2 of this class, we are still going to touch on the other aspect of mathematics, and that's in respect of ML. But sometimes you have to pre-process. When you are doing ML, you have your data. The data has to be pre-processed. That may require you to build unique algorithms. Citing my own experience, I was using the data signal processing, which are native to electrical engineering. I was applying them to process DNA sequences. DNA sequences are alphabets, ATCG. And of course, the ATCG actually represents molecular compounds. So, and you cannot push ATCG into your neural network. It's a numerical platform. So I needed to do an encoding. And of course, that took me to the relative molecular masses of those compounds in order to encode the ATCG. And after I've done the encoding, of course, it became easy to apply cosine distance and all of the other. I did Pearson correlation coefficient and all of those in order to properly capture the non-correlated component, doing features extraction now. So your problem is what will determine the mathematical or life science concept that you are going to need. In fact, at the time I had to transform those sequences to images so that I can apply image processing algorithms. So trying to convert from DNA to images, I had to go into Z transform, which is a mathematical concept, and that's a pre-processing phase. So your problem is what will determine
set of tools.
Exactly, but this is like whetting your appetite.
Yeah.
Such when you are confronted, you know how to navigate. When you are confronted with such use cases, you know how to navigate. So that's just my own contribution to that. Thank you.
Excellent, Prof. Thank you. You know, I said before that this is just the beginning, you know. So, you know, I believe Professor Adetiba will come up, you know, with other fora workshops where we can also talk more about this and I know further discuss important concepts. Okay. Don't worry. Don't be pushed away. Like I said, when you are still starting research, you are just a beginning researchers. Don't worry. See, you have to learn a number of things. It's always like that. Okay. For every new researcher, beginning researcher is always like that. You have to learn new things, a number of things, concept. Okay. All right. Until you become a full-fledged researcher, really. And then when you do your PhD and then okay, you become a full-fledged researcher. Having gone through all of these concepts and learned all of these tools, just turn out to be an excellent researcher with so many tools in your toolbox. Thank you.
put our hands together for our facilitation so far. It's been great. Thank you. We'll be starting off in this session. So we'll start off by completing the part 1 lecture, and then we'll start part 2 immediately. So Dr. Awelewa, you're welcome once again.
Yeah, thank you very much, Dr. Oshin, for your good moderation. I also want to thank Professor Adetiba again, and thank you, the audience, for also keeping faith with us. So let's look at the last part of this part 1. Here, we want to look at eigenvalues and eigenvectors. Eigenvalues and eigenvectors. This, if you have not gained anything so far, make sure you don't miss this, because this part is extremely important. Very, very, very important. Okay, because when we say eigen, we mean characteristic. Okay, the values that are characteristic to your system, to your device, to your process, they are very characteristic. Okay, in the sense that if you have access to these values, you can gain a lot of insight about the solution, the system you are actually looking at. Extremely important. And these values, fortunately, have associated vectors, and we call these vectors eigenvectors. Together, these two are extremely important in so many applications. In control system, they have their wide applications. Like I mentioned before, in principal component analysis, which for dimensionality reduction, they have a very wide application. I also know in some other fields like face recognition, where you talk about eigen faces, and what have you. Very, very, very important. Very, very important, because if you have a matrix, you can always create a similar matrix, a matrix that is similar to that, and use that matrix. Okay, so I'm going to introduce the fundamentals of this right here, and then you can explore this further on your own. Let's look at this equation here. Okay, remember the last discussion on a linear transformation, okay, where you use a matrix to actually move from one space to another. Okay, so this is a transformation now. It's another linear transformation, but this one is very, very unique now. This is very unique. You can see AX here. Look at AX here equals to lambda X. AX equal to lambda S. The other one we look at the other time. Look at it here. AX equals to Y. Okay. You multiply a matrix and a vector together, you get a new vector. Okay. Whose direction is different, and magnitude is also different. Okay. AX equals to Y. So this transformation can give you a reduced space. It can give you an increased space, like I mentioned before, depending on the new dimension you have here. But if you look at this linear transformation, AS equals to lambda S, all right? You have AX right here, the product, and the result is also lambda S. If you look at it very well, okay, you see this, right? Look at the direction, look at the original X. Okay, you are still keeping that same X here. That same X is still being kept. The only thing that is changing now is just the magnitude. You see, the magnitude is changing. Can you see how important this is? Look at this A. It looks big. This is a big guy that is multiplying this vector. Now look at okay. What it means now, it now reduces to a small guy multiplying the same vector. big guy multiplying a big small guy here equals to a small guy multiplying a small guy. Okay, this is very, very, very interesting, and this can only happen under certain conditions. Okay, it can only happen. Linear transformation generally is like this. You change from one space to the other generally, but there is a particular one. It's just like a critical point now, a singularity point, a unique point at which the entire matrix can be replaced by a very small, tiny part of the entire system. Just like lambda. Look at this, lambda is now replacing a very big part, an entire part. Okay, this is why this is so important. This is so important. And this value here is very important because it's actually representing this A. Okay, it's just like you are using a scalar, so to speak, to capture A. All right, and that's why we say it's eigen characteristic. This is characteristic to, okay, the system, to the matrix. AX equals to lambda X. So you can see A is n by n. Okay, this is the first instance we are looking at. A is n by n. Later, we are going to look at the other one, which is a singular value decomposition. That can happen, okay, to a non-square. This is a square matrix now. So A is an element of n by n dimensional matrices, okay, an element of that space. X is n by 1. Okay, now AS equals to lambda X. Okay, so X is what we call the eigenvector. Lambda is what we call an eigenvalue. So the two of them form an eigenpair. They form an eigenpair. Okay, the two together plays a major role in system analysis, and then processing. Let's look at this further. Because A has an order of n. From here, you can see A has an order of n. Okay, so there are always n number of this lambda, okay, any number of this that goes with this A. Okay, so we normally have n of these, n eigenvalues, okay, because A is an n by n. Okay, so in that case, we can expand this AX equals to lambda X, okay, in an explicit way. In an explicit way as follows. Look at it. If the first lambda is lambda 1, first eigenvalue, then we can write this equation. And then in a compact form, we can write them as this. In a compact form. I want us to look at this one very well. Okay, this equation represents all of this now. Okay, we're having A, see A is common to all of this. X is here, Xi is here, okay? So X is like a concatenation of these vectors x1, x2, xn. Okay, so we call this a matrix of eigenvectors, AX, a matrix of eigenvectors. Okay, so if you multiply A by the first vector element, which is x1, we have AX1. Similarly, A by the second, we have AX2. Okay, then we arrange this part such that these equations here can be still valid. All right, so we also have x1, x2, xn. So we create the same matrix of eigenvectors, okay, as X. But now we bring in all of these lambda i's by creating a diagonal matrix whose diagonal elements are lambda i's. The I equals to 1 to n. Okay, this is a diagonal matrix. Okay, You can quickly right there, just assume that you have two equations, okay, x1, x2, here, lambda 1, lambda 2, and then you can justify, you can actually confirm this quickly, okay? You have a diagonal matrix. The diagonal elements are simply lambda 1, lambda 2. X is made up of x1, x2, okay? And then you can check to see that these equations are verified. So this is a compact way of writing this, all right? So we have all the eigenvectors here, and then we have all the eigenvalues captured here. Okay, we can, so as you can see now, you can see x common here, x common here. And then we have a matrix A, and then we have a new matrix, matrix lambda, big lambda here, all right? We can write this further as this. I want us to see AX equals to X lambda. That is equivalent to A equals to X lambda X raised to power minus 1. Can you see? That is, if you pre-multiply both sides by the inverse of A, this is what we are going to write. In order to make A the subject of the formula here, rather you post multiply both sides by the inverse of X. We want to eliminate this, so we find the inverse of X, we post multiply both sides of this equation by it. So that will give us this. Okay, that is the way to make A the subject of the formula here. So you can see what we have. A equals to the matrix of eigenvectors multiplied by a diagonal matrix made up of all eigenvalues multiplied by the inverse of the matrix of eigenvectors. Okay, very, very important. This is a decomposition. Here we have decomposed A actually, and we call this eigenvalue or spectral decomposition. Eigenvalue or spectral decomposition. We can see this is A, and then we're having a matrix that is similar to it. A, C lambda. Okay, very, very important. Meanwhile, before I proceed, let me quickly point out that because X is on the right of A, we call this eigenvector the right eigenvector. I want you to pay attention to that because we'll come to that shortly. The right eigenvector, you can see X is at the right here. Okay, right eigenvector. We also normally call this X the matrix of a right eigenvector. Okay, so this is the popular spectral decomposition. The eigenvalues tell us a lot about that matrix. Okay? If the matrix is behaving well, you can tell from the values of the eigenvalues. If the matrix is not behaving well, you can tell from the values of the eigenvalue. Okay, the frequency nature of A and then the frequency nature of the system A represent can actually be gleaned by understanding or by looking at the eigenvalues. Okay, and that is why we use spectra. That is from spectrum, and spectrum, of course, frequency spectrum. Okay. So this is the popular eigenvalue decomposition. Okay, so we can always decompose A into a diagonalized form, which is this one. Okay, there are cases where we decide to use this instead of A. There are many cases where we prefer to just use this instead of A. Okay. This is good. So we normally say that, as you can see, that you can also do, this is A, you can also find lambda, okay, and then you have this. Difficult to make a lambda the subject right here, okay, just take X, okay, and then pre-multiply both sides by the inverse of X. If you pre-multiply both sides by the inverse of X, you'll be able to eliminate this X, okay. And doing that here will make you to have inverse of X here times C times X, which is what we have here. Okay. Also in linear algebra, we say that matrices that have this characteristic are actually called similar matrices. We call them similar matrices. This means that we can always find a transformation matrix X, okay, such that A and then lambda can be represented as this. So it means that this lambda and A are similar. We call them similar matrix, and they are related by this similarity transformation matrix X. Okay, so I said generally, this is it. Generally, this is it. A, P, and P inverse, okay, can always be related by this. Okay, all right, where this A tilde is a similar form of A. If you can find a matrix P like this, such that this equation holds, then A tilde and A are similar, just like we have here. Okay, so spectral decomposition actually leads to similarity matrices A and lambda. Okay, so this is the first thing you have to note under eigenvalues and then eigenvectors. Eigenvalue decomposition, you can actually find a similar version of a matrix, an n by n matrix or a square matrix, okay, by finding the eigenvalues and the eigenvectors of the matrix. First thing to note right there, okay. Another thing to know here is that we can also write, excuse me, we can also write, you see the same equation, we can also write another form. This is the form I call, okay, right eigenvector form, because of the position, the direction of this X here. You can see, don't forget S is n by 1 here, you can see, so that matrix multiplication is conformable. You see, A is n by n, S is n by 1. So the result, of course, is n by 1 vector multiplied by lambda. Okay, so this is one form, this one version. All right, another one is to actually bring a row matrix here before A. A row matrix, I mean a row vector before A. Okay, like this. Like this, you see? You now have, it's also possible to have another linear transformation such that a row vector pre-multiplies a square matrix. It's also possible to have this such that you'll be having this small guy multiplying this big guy, giving us a small guy multiplying a small guy. This is another version of what we had before. So we call this Y here a left eigenvector. Left eigenvector of A. There is right eigenvector of A. Don't forget. So you can write a corresponding spectral decomposition, okay, in terms of left eigenvector, right eigenvectors. Then we can write the same for the left eigenvector as this. If you are using left eigenvectors, this is the decomposition. A equals to this, inverse of the matrix of left eigenvectors. Okay, so in this case now you are just going to arrange these left eigenvectors vertically. Okay, so it means that the first row of this of Y is actually the first left eigenvector. The second row is the second left eigenvector up to the last row. Okay, but unlike this, okay, unlike X, this is arranged in a column fashion. The first column is a right eigenvector. The second column is a second right eigenvector. The third column, okay, is the third right eigenvector, etc., up to the last. Okay, so that is the difference. So I want you to take note of the difference between this and this. Okay, the two of them are valid. The two of them are valid. Okay, so we normally say that, we normally conclude that if that is the case, that these two equations are valid, look at it, these two equations are valid. A equals to x lambda x raised to power minus 1, okay? And then inverse of y times lambda, okay, times y. Of course, we can deduce immediately that this x here, okay, actually equals to this y inverse here. All right? And then the x inverse there, okay, is actually equals to the y here. Okay. So we can write that x y inverse, x equals to y inverse, x equals to y inverse. We can write that. Okay, and then we can write x times y equals to I, which is an identity matrix. I want you to see that quickly. If we can do this, okay, x here equals to this y inverse here, okay, it means that xy equals to I, an identity matrix. I hope we can all confirm that. So another equation to note is that the matrix of right eigenvectors times the matrix of left eigenvectors equals to an identity matrix. Equals to an identity matrix. Okay, I didn't include that here. I don't know why, but just take note of that. Okay, the matrix of the right eigenvectors, which is x, times the matrix of the left eigenvectors, which is y, always gives an identity matrix. Okay, and then from there, we can write the following. From that last equation, x, y equals to I, an identity matrix, we can deduce the following, what we have on this slide. Okay, that the left and right eigenvectors corresponding to different eigenvalues are orthogonal. The left and right eigenvectors corresponding to different eigenvalues are orthogonal. Okay, we can deduce that from x times y equals to I. Okay, so this is it. If lambda I and lambda j are two different eigenvalues, okay, two different eigenvalues, okay, then the corresponding eigenvalue, okay, of lambda I is actually, okay, if this is left, okay, then the corresponding eigenvalue is yi, all right? Okay, because we have left and right eigenvector. So, right, so for this, all right, yi, and then for this, xj, okay? So the eigenvectors product corresponding to this is actually orthogonal. So this is what we have, okay? yi times xj, okay? Yi is the left eigenvector that corresponds to this eigenvalue, okay? And then xj is the right eigenvector corresponding to this. So when you multiply these two together, you are going to get 0. And you can deduce that from that equation, x times y equals to I. You can deduce that, okay? So this is very, very important. You see, I use orthogonal. Remember our earlier definition of orthogonality, okay? When two vectors are orthogonal. Just like somebody asked that when they are perpendicular, okay? We can also state that the product of left and right eigenvectors corresponding to the same eigenvalues equals to a constant value. Okay? Yes. All right? So look at this. yi, xi. Okay? This is a product of left eigenvector and write eigenvector corresponding to the same eigenvalue. You can see that I'm using II here. Okay, so if you are multiplying these two together, you are going to get a constant value. Okay, in fact, 1. In fact, 1, because when you look at that equation again, x times y equals to an identity matrix. You can deduce this equation. Okay, so I want you to take note of this too. All right, you have left eigenvectors, right eigenvectors. This is always valid. If you are multiplying left eigenvector and right eigenvector corresponding to an eigenvalue, the result is always 1. The result is always 1, okay? But if you are doing that for different eigenvalues, of course, the result is always 0. Okay? So you need to pay attention. You need to pay attention to this. Very, very important. Okay. So apart from apart from the relevance of eigenvalues and then eigenvectors, there is also another concept which is very, very important. Okay. You always want to know the influence of the component of A on the eigenvalue. If we know that eigenvalues are very important, that they portray important information about the matrix, then how are the elements of A? How do they influence the eigenvalues? How? So we talked about eigenvalue sensitivity. Eigenvalue sensitivity. Okay. What is the sensitivity of matrix A eigenvalues? All right, to the elements of A. Okay, how do the elements of A influence the eigenvalues of A? Okay, this is also good to know. All right, this is also good to know in many of our analysis and then signal processing. We want to know which elements of A are actually determining, which ones are dominant, which ones are actually dominant element in the sense that they influence the eigenvalues more. Okay, so that takes us to the next one, eigenvalue sensitivity. Eigenvalue sensitivity. Okay, and this is the way to do this. Again, you also have to pay a little attention here, right? Remember this equation, okay? The same equation we had before. This is the right eigenvector. We can see this is the right eigenvector. AXI equals to lambda I, AXI. Okay, so in order to find the sensitivity of lambda I now, okay, so the elements of A, this is the way we normally do it, okay? Right, that is, how does this lambda I change as the elements of A change? Okay, so when we talk about change, now we are bringing in the calculus. Professor Adetiba mentioned calculus the other time. So we want to find this change. How does lambda I change as a result of the element of this? So we talk about differentiation, calculus now. Okay, so let's differentiate and see what happens. Let's differentiate this equation with respect to a particular element of A. Let's do that. If we do that, what are we going to have? All right. So that brings us the concept of a partial differentiation here. Okay. I was thinking whether to introduce this when I'll be discussing partial differentiation or to. I was actually in a dilemma, but because this is closely tied to this discussion is closely tied to these eigenvalues and eigenvector, eventually I had to decide to keep this here. Okay, but this we can understand now. I will explain this so that we can understand this. But when we get to the second part, I'm going to explain partial differentiation in more detail. So here we simply find the differentiation of both sides of this equation with respect to an element of A, and this element of A is AKJ. Again, don't forget we are talking about eigenvalue sensitivity. okay, the sensitivity of this eigenvalue, okay, to the elements of this A. AKJ is used here to represent a particular element of A. Okay, so you remember our calculus, okay? In order to differentiate this, okay, we differentiate A with respect to this element, we keep xi constant, and then we keep A constant, and then we differentiate okay, xi with respect to AKJ. Believe we are all familiar with this, okay? The product rule, right? In calculus. So similarly here, we differentiate, okay, this lambda I with respect to AKJ, and we keep xi constant. This is what we have here. Plus, we keep lambda I constant, and then we differentiate xi with respect to AKJ, okay? All right, so if you perform the differentiation, this is what we are going to have, okay? This is what we are looking for. We are looking for this. This is the sensitivity. We want to find, okay, rate of change of lambda I with respect to AKJ, okay? So this is what we want. So we proceed further, okay? Here, because we want to do some elimination, so we multiply both sides of this by yi, okay, which is the left eigenvector, okay? By the time you see this, you understand, follow to the end, you understand why I multiply both sides by this yi, okay? All right, so if you multiply yi, okay, by both sides, multiply both sides rather by yi, this is what we have. We have yi times this, yi times this, yi times this, and yi times this, okay? And then we can now combine this, we combine this, okay, and this. We're having this, which is this, okay? We're having this, which is this. We are combining this and this to have this, okay? And you can see that it's not difficult to see.
Hello, Doc.
Yeah,
You
Prof.
may want to also let the audience know why you introduce an identity matrix there to help understand that equation properly.
Okay. The other equation there, right?
No, I mean the identity matrix.
Oh, yes, yes. Okay, okay, good. Okay, sir. Okay, okay. Okay. So let's take this, all right, to this side. Okay. When you take this to this side, you see partial of xi with respect to AKJ is common. We take it out, all right? Yi is also common. We bring it out there. I want you to take note of this. Look at this, yi is a vector. Look at this also, all right? This is a vector. Okay, so this is left, so it maintains left here. Why this is right? It maintains right here. But I want you to see something. You see that there was no I sort of here, right? Before. Okay, but now we're introducing this I. If you didn't introduce this I, it means you'll be subtracting a scalar. Okay, you're subtracting a matrix from a scalar, which is an invalid operation. It's an invalid operation. So in order to capture this appropriately, we just had this I here, and then you can see that this lambda I is just along, it's just the same number. Okay, the same number running through the entire diagonal. So it doesn't really change anything. Okay, it's just the same I is running through the diagonal. So it still keeps the original information, but now we're actually obeying an arithmetic equation here, because this now becomes a matrix. A now is being deducted from a matrix in this case. Okay, so one step now, and then we'll be through with this. I want you to look at this very well. Look at this very well. Yi lambda I, okay, capital I minus A. Okay, this is our earlier equation. Let me show you here. This is this equation. Okay, this is this equation here. Here is a yi, okay, equals to lambda I, which is the same thing as lambda I. Here, you can see, okay, lambda I minus A in parentheses now, and then y outside the parentheses here. Okay, please, I want you to look at this. Take this one from here to this side. You are going to have 0 equals to lambda I minus ya. Okay, because y is common, then you take y out here, and then you have lambda I minus a here. So it means 0 equals to this. 0 equals to this. Okay, 0 equals to yi, right? Lambda I minus a. So what we have here is actually equals to 0. This is actually 0. Okay, leaving us with this. Leaving us with this. Or rather, please, one more thing to say, okay, before we arrive at this. Okay, I want to again to look at this to see this very well. All right, we see lambda I with respect to AKJ here, okay, and then we see yi, and then we see xi here. Okay, I want you to look at these two, yi, this over this, multiply by xi. Are we together? So let's look at this very well. You know, A is made up of constant elements. Okay, A is made up of constant elements, and AKJ is one of these elements. It's at a particular entry in A. So if you are differentiating A with respect to this AKJ, particular element in A, that is the only point that will be 1. Every other one will be 0. If you differentiate A with respect to A12, element on A12, okay, that entry will be 1. The other one will be 0. Okay, the other one will be 0. All right, so that gives us a way to re-express this. That gives us a way to re-express this. Okay, so what we are trying to say here right now is you now have a matrix here that is made up of a lot of 0 entries. Okay, but only one point. Only one point actually has a value, which is a unity. Okay, so if we multiply, the idea is now, look at this. This is a row vector. This is a row vector yi. This is a column vector xi. So if you multiply this by this, okay, and you multiply this by this, look at this. This is 1 by n. This yi has a dimension 1 by n. So if you multiply that 1 by n by this, which is n by n, okay, you are going to have 1 by n. Are you with me? You are going to have 1 by n. And then if you multiply that 1 by n vector again by this xi, which is n by 1, you are going to have 1 by 1. You are going to have 1 by 1. Okay, so that leads us to this. That will lead us to this, because this is going to be 1 by 1. When you multiply these together, eventually you are going to have this. Okay, because of the nature of this. All right, and then you now have this. Of course, we can deduce this immediately. All of us can see this immediately, that is equals to this. because this is yi and this is xi. And remember, don't look at this as a matrix because this is just a scalar. Lambda is a scalar. Okay, so you can take yi to this point, yi times xi. And then you come back to this one, yi times xi, which is 1. Okay, so this is now 1 times lambda, partial of lambda I with respect to partial of AKJ. That is what leads us to this, okay? All right, but I want you to take note of this. The derivation you may follow later, okay? But you have to understand this. So you can find the sensitivity of an eigenvalue lambda I. All right, if you are working in this area, you can actually check how lambda I, the eigenvalues are actually changing with respect to the elements of your system matrix. This is how you find, and then you can actually categorize them, okay, according to their level of dominance. Now, so this is the way to find. You can see the product, okay, lambda, partial of lambda I, with respect to partial of AKJ, will give us yi kj times xji, okay? If you your own, if you look at, please, I want you to look at this matrix and use like a 2 by 2, and then you will see, okay, that this is actually the case. Okay, so we are saying that, remember, y is a row vector. Y is a row vector. So y is a row vector. So we are saying that y ik, okay, is actually the element on the ith row and then the kth column. Okay. All right. Don't forget, left eigenvectors are not are many, depending on the order of the system. If the order of the system is 3, I told you before, you have 3 eigenvalues, and then you have 3 eigenvectors too. Okay. So here now, if n is 3, it means we have 3 left eigenvectors, we have 3 right eigenvectors. Okay, so for instance, if you are looking at, let's say, want to find the sensitivity of eigenvalue 2, okay, eigenvalue 2 with respect to element on row 2 and then column 3, for instance, row 2 and column 3. Okay, how does this element on row 2, column 3 influence lambda 2? Okay, the result will be y2, 2. Okay, y2, 2. That is the second left eigenvector. All right, and then the element on the kth column. That's what we have here. And then similarly, okay, similarly, the element on this row J, all right? Remember, this is a column, okay? It's a column vector. The right eigenvector is a column vector. So the element on row J, all right? Okay, multiply by, all right, multiply by that column pi, okay, which is actually the number of, the eigenvalue that is right there. If it's second eigenvalue, so it's going to be 2. If it is third, it's going to be 2. So you multiply these two together, you are going to have an idea about how this element influences this eigenvalue. So you can actually calculate all of this, right? You can find all of this. For instance, if you have a 3 by 3 matrix, so you have 3 eigenvalues. And then you have 9 elements, because it's a 3 by 3 matrix, 9 elements. So you can find the sensitivity of each eigenvalue with respect to all of these 9 elements. Okay, and then you have a number of things right there. So you can actually determine which one influences the eigenvalues more. Okay.
Okay, Dr. Awelewa, there's a question in the box.
Okay.
Which I think you need to pay attention to. And
Okay.
also, in respect of the sensitivity of the elements to the EigenValues,
yes, sir.
What's the range? What's the range for the sensitivity, such that when you have such a range, you will know if that element is extremely sensitive to the eigenvalue or it is not sensitive to the eigenvalue? So that's the question.
Okay, good. It actually depends. You know, it depends on the systems you are dealing with now. So it's not actually constant for all systems because eigenvalues are different for all systems, all devices, all applications. Okay, so you can't say that it has to be this fixed range. Okay, no, it depends on the application. But when you calculate, one thing is when you find the sensitivity of this eigenvalue, when you look at all of these numbers, okay, you can see their size. You can see their size. For instance, if the rate of change of eigenvalue 2, okay, with respect to element A22, all right, is 10. Can you see the rate of change? It means it's changing very fast. All right, the rate of change is 10. This is calculus, changing very fast. If the other one is like, for instance, 2, okay, you can see the rate of change is 2. Okay, it's just 2. It's slower. The one with time is lag. The rate of change is lag. It's changing very fast. Okay, for instance, look at it as like a gradient. Okay, the gradient of one is greater than the other. The rate of change now, that is the key. Okay, and it depends on the systems. Okay, because systems are different generally. Systems are not the same. And they also have different eigenvalues. Systems do not have the same eigenvalues. Okay.
Okay, the question the student is asking inside the box.
Okay.
I guess, yeah, you can just, I think Julius was asking a question somewhere.
Okay, Julius, okay.
Yeah. He's saying, I still don't understand why we have to differentiate with respect to AKJ. Where is it coming from? But I think with the explanation you have given, maybe he has now understood.
Okay.
I don't know. He can talk by himself if he's still there.
Julius, is that clear now? Okay,
yes,
thank you. Okay, thank you. Thank you. Like I said again, you can explore these things further, please. Okay, you can explore these things further. All right, when you do that, and then when you are reading papers related to where some of these concepts are utilized, you'll be able to understand better. Okay, I think that's one of the, one of the ideas here. I've actually used this in some of my control algorithms before. Okay, where I had to take advantage of this. Okay, to check the dominance, check the sensitivity. All right, and then I paid attention to those ones that dominated the dynamics of the system. Okay, and the ones that vanished away quickly. Okay, if you are vanishing away from the dynamics, and then there are ones that are taking time. Oh, I better pay attention to the ones that are taking time. You know, they are the most dangerous ones. Okay, the ones that vanish away quickly, I can, I can just ignore them if they, if they vanish away such that the range of, the range of active response of my system, okay, is not affected. For instance, if my system is just taking starting on from I is equals to 0, for instance, and it's getting to like from t is equals to 0 and it's getting to like t is equals to 20. That's t is equals to 20 is the final stage. And then at t is equals to 0, 1, okay, some parameters are already vanishing away. All right, I may decide not to pay attention to those ones and then approximate my system based on the ones that are influencing the dynamics at like t is equals to 15, 16, 17 up to 20. Okay. You know, it's just a trick here in system design and analysis and signal processing. These are some of the tricks we play. Okay. and then we'll come up with a simplified, reduced systems. Okay, but they have basis, they have a foundational, assumption which is valid.
We have a question here.
Okay.
Yes, sir. Thank you so much for my name is Udeme. Yes,
okay, Udeme, how are you?
Very fine, sir. Thank you so much for the detailed explanation. But just a clarification on the last equation where we have y, I, k, and a subscript and x and ji. Since y and x, you had mentioned that y is a row vector and then x is a
column vector.
Yes, why are the subscripts multidimensional?
Okay, very good. Yeah, that's a good question. Okay, again, I I want you to pay attention to the fact that, let me use this. Let's use a 2 by 2. If A is 2 by 2 now, okay, our eigenvalues will be 2. Our eigenvectors will be 2. Are we together? Yes. So if eigenvectors are 2, okay, all right. So it means that if we have yik, let's say we have y12, okay, y12. So we are talking about the first eigenvector, okay, and then the element on the kth column in the first eigenvector. If I is equals to 2, we are talking about the second eigenvector and then the element on the kth column. All right. Okay. The first index here refers to the left eigenvector. Okay, whether it is the first, second, or third, or n, depending on the order of the system. Okay. Similarly, this, right? We have 2 column vectors, eigenvectors, because it's a 2 by 2. Okay. If J is 2, for instance, it means we are referring to the second right eigenvector now. Okay. And then the elements, of course, and then the element on I. Okay. Are we together? Udeme?
Yes. Yes, sir. Yes, sir.
Can you see that? It's because of the number of eigenvectors that we have. Okay. And that is what we're actually using here. Okay. You may have to go over these things later, really. Okay.
Let me just also add that of course, before the advent of deep learning, now we know with deep learning and generative AI,
yes, sir.
The deeper, the more data you have, and the deeper your network, the better the performance. That is the era we are in. But before we got to this stage, there usually there was always need to do dimensionality reduction.
Yeah.
And that is what we call features engineering.
Okay.
Features engineering. So currently in deep learning, that feature engineering is done automatically within the architecture of the network.
Okay.
But prior to that, you have to do manual feature engineering.
Okay.
Exactly. And that will involve maybe, for instance, you have an image, which is a matrix. If it is a grayscale image, that matrix will be a two-dimensional matrix, and the values will range from 0 to 255 for a grayscale image. And by the time, assuming you have a 1000 by 1000 pixel size, that is going to give you like 10,000 pixels elements. So if you want to build a shallow neural network, it means we need like 10,000 neurons in the input layer for you to be able to capture that image properly. Okay, so back then you have to do dimensionality reduction.
Yeah.
And using this concept of EigenVectors and EigenValues, by the time you compute the EigenValues, you are able to know the principal. That's why they call it characteristics values. You are able to know the principal vectors that can actually distinguish that particular face from every other face, every other faces that you have within your data set. And instead of having like maybe 100 by 100, you may eventually come up with maybe like 10 by 10 after you have computed the principal eigenvalues. Maybe there are 10 of them, so you pick the corresponding eigenvectors, and you can be too sure that those 10 by 10 are vectors. They will represent almost accurately the 100 by 100 matrix. So
correct.
that is one of the major areas of application of this concept.
Correct.
And that is what they done with principal component analysis, which used to be a go-to for dimensionality reduction in AI space.
Okay.
But thank God for cloud computing. Thank God for deep architectures.
Thank God for experts who have taken
exactly. But it still boils down to incorporating this concept inside these new network architectures.
Really.
So exactly. So
thank you, Prof. Thank you for shedding more light. Okay. Like Prof has said, so these things are very applicable. They are very, very useful. Okay. That will actually also help you to know the way your system behaves, to understand your system in a deeper way. Okay, having to know some of these concepts, will enable you to have this deeper understanding. Okay, it's very, very useful. Very up till today, this is still very useful. EigenVectors, values. So many things that you can do with the systems. Okay, so many manipulations and reductions and and what have you. Okay, so thank you, Prof. Thank you for that. Good one. Okay, can I proceed, Dr. Oshin? All right.
Yes, sir.
Okay. Right, so this is just about calculations of eigenvalues, eigenvectors now. Okay, this is just to let you know how this is done, but most of the time you have to use the software packages like the Python, the MATLAB to do all of this. This is just to let you know how these calculations are done. Okay, again, if you have this matrix, okay, and then these equations, this equation emerge from here, okay, AXI, okay, you have these equations. This is not just one, we have a number of them, okay, depending on the order of the system. Okay, if we have two eigenvalues, we write the first equation, lambda 1 I minus a, x 1 equals to 0. And then we write the second one, lambda 2I minus a into x2 is equals to 0. All right, and then you can solve these equations, you can solve them, and then find the values of lambda I and then xi. Okay, right? But the way it is here, we can actually make xi the subject of the formula. That is, we can find xi from here. That will give us this. Okay. The way to do this, to find xi, is to eliminate lambda I minus a here, right? By multiplying both sides by the inverse of this. Okay. If you do that, you are going to eliminate this, and then that inverse will come here. Right, and the inverse is the same thing as the adjoint all over determinant. That is why you have it like this. Okay. This is a trivial solution. If you go on the surface, you see this is just 0 because everything is multiplying 0 here, and then you conclude that xi is 0. right? But not, there is a point at which a determinant of a lambda I minus A equals to 0. That point is a critical point, an important point, where this equation has a different meaning. Okay, that is where xi is not 0 now. Okay, if determinant, the denominator here is actually 0, okay, then this becomes 0 by 0, which is undefined, really. All right, so at that point, this is, we'll be having xi that is non-zero. Okay, this is also very important, because when the determinant of a lambda I minus A equals to 0, then we can determine the values of lambda I that satisfy that equation. Okay, and that will give us a set of eigenvalues, okay, that represent the system, or eigenvalues which characterize the system. Okay, we find the determinant of this, which is this. Okay, right? Determinant of lambda I minus A, right? And then to find the eigenvectors, we solve this equation. Okay, which is the equation I discussed here. To find xi, you solve this equation. All right, and then to find the eigenvalues, you solve these equations. Okay, so in order to determine eigenvalues and eigenvectors, what we do is to find this and determine eigenvalues, and then you solve this equation and find the corresponding eigenvector. Okay, this is how it is done in a basic way. Okay, but the values of eigenvalues also give further information about the nature of the eigenvectors. Okay, for instance, if the eigenvalues are distinct, then the eigenvectors are distinct. When I say the eigenvectors are distinct, I'm saying that all the eigenvectors are linearly independent. Again, linear independence now. It means all the eigenvectors are linearly independent when the eigenvalues are distinct. Okay, and then we can apply these equations directly. We can solve for xi directly here, and that will give us, and then we can compute xi from there. Okay, another way to also do this is to find any non-zero column of this matrix. Okay. All right. All right. You may be wondering how that. Okay. So you may want to explore that. Further. Okay. This a whole discussion on this. Okay, but this is also another way to find the eigenvector when the eigenvalues are distinct. Okay, but when the eigenvalues are not distinct, when they are repeated, okay, we have a situation. Okay, for instance, if we have 3 eigenvalues, okay, and they are lambda 1, and then lambda 2, that is 2, 2, 1. 3 eigenvalues, and we have 2, 2, 1. Okay, it means the first eigenvalue has a multiplicity of 2, or it is repeated twice. Okay, so it means that the eigenvectors of this eigenvalue may be dependent, may be non-dependent. Okay, it depends on the particular condition. All right, because naturally they are distinct. Okay, of course you know immediately that, okay, because this eigenvalue is distinct, then and a distinct eigenvector should go with it. But if you have eigenvalues now that are similar, that are the same, okay, does it mean that the eigenvectors are also the same? Okay, so we have a condition for determining this. Okay, I wrote here that the number of linearly independent eigenvectors associated with a given eigenvalue lambda I, which is repeated Ri times, just like the one I mentioned, 2, 2, 1, eigenvalue 2 is repeated twice now. Okay, so we can determine the number of eigenvectors of these eigenvalues that are linearly independent. We can determine them. Okay, again, as an example, we have lambda equals to 2, 2, 2. 2, 2, 1. That is, there are 3 of them. The first one is repeated twice. Okay, the last one is unique. The unique one will have a unique eigenvector. Okay, a unique eigenvector. But the first 2, because the eigenvalues are the same, they are eigenvectors now, of course, which are 2. But these 2 eigenvectors you don't know normally if they are linearly independent or they are dependent. So one condition in linear algebra to determine this is this equation. Okay, it's extremely important in determining that. All right, Pi is what we refer to as the number of linearly independent eigenvectors that is associated with this repeated eigenvalue. Okay, and it is determined as n minus rank of lambda I minus a. N is the order of the system. Okay, lambda I minus a is actually the characteristic matrix which we talked about before. So we find the rank of this when we substituted the value of this lambda I. Okay, and then we subtract that from n. That will give us the number of linearly independent eigenvectors. Okay, right? And this is between 1 and Ri. Pi is between 1 and Ri. R is the number of times this lambda I, okay, is repeated. Okay, the second, the first one here is possible for the eigenvectors to be linearly independent. It's very possible. Okay, even if the eigenvalues are not distinct. All right, this is one situation is possible, depending on the system, the nature of the matrix. That is going to determine that. Okay, but we have been able to find and establish this. Okay, for certain system matrices, it is possible for the eigenvectors associated with a repeated eigenvalue to still be linearly independent. And that is governed by this equation, as I said. So the other one is when it is just 1. That is not 1, is not R, but it's in between. Okay, so that is the condition for determining this. Okay, and this idea is used in so many, matrix decomposition concepts. Okay, but thank God we have many of these software packages that have these algorithms inbuilt. They have this inbuilt, so you can just apply them and go ahead, with okay. With your work without having to bother yourself with the algorithm that is running, behind all of this. But it's still good to know where this actually coming from. Okay. Here we just have a, okay, not this. So we have a code to calculate eigenvalues and eigenvectors here. Okay. All right. These are not, all of these are not difficult, okay? Use EIG, E-I-G, okay? And that will give you the eigenvalues and then the eigenvectors, okay? Without much ado, right? And you can always form the diagonal form of A or a similar version of A by just doing this, okay? All right, or you use another approach for doing that. Okay. All right, that is the end of part 1.